When we look up into the night sky, the sight of countless stars twinkling in the distance sparks a deep sense of wonder. What we are seeing is only a small fraction of the immense cosmic structure we call the Milky Way Galaxy, our home in the universe. The Milky Way is not just a random scattering of stars but a vast, dynamic system full of mystery, beauty, and complexity. Its formation, structure, and role in the cosmos have captivated scientists and stargazers alike for centuries. Yet, despite centuries of study, it remains one of the most enigmatic and awe-inspiring objects in the observable universe. The Milky Way is a barred spiral galaxy, spanning about 100,000 light-years in diameter, with around 100 billion stars, gas clouds, dust, dark matter, and planetary systems. The central hub of the galaxy contains a supermassive black hole, a powerful entity that exerts a tremendous gravitational pull on everything around it. This black hole, Sagittarius A*, is a central player in shaping the dynamics of the galaxy's inner regions. The structure of the Milky Way itself, like other spiral galaxies, consists of a flat rotating disk of stars, gas, and dust, surrounded by a spherical halo of older stars and star clusters, called globular clusters, along with an elusive dark matter component that holds the galaxy together. For ancient civilizations, the Milky Way appeared as a cloudy band stretching across the sky, and it wasn't until Galileo Galilei's observations through his telescope in the 17th century that humans began to understand that this band was composed of individual stars. Over time, technological advancements have allowed astronomers to explore deeper into this cosmic expanse, unveiling its true nature. Our galaxy is one of hundreds of billions within the observable universe, each with its own set of unique characteristics, yet the Milky Way stands out because it is our galactic home, a place where our sun, planets, and all known life reside. The formation of the Milky Way is a story that spans billions of years. It began over 13 billion years ago, soon after the Big Bang, when vast clouds of gas and dark matter began to coalesce due to gravitational attraction. This process of collapse and star formation created the first stars in our galaxy, and over time, the galaxy grew as it merged with smaller proto-galaxies and collected more material from the surrounding universe. The violent collisions between these early structures gave rise to the Milky Way's current shape, along with its stars, planets, and other celestial objects. Despite its mature and seemingly tranquil appearance today, the galaxy continues to evolve and undergoes constant changes as it interacts with its cosmic environment. The Milky Way's structure is defined by its spiral arms, which extend outward from the central bulge in a beautiful swirling pattern. These spiral arms are regions of active star formation, where clouds of gas collapse to form new stars. The Sun, along with its planetary system, is located in one of these arms, the Orion Arm, about 27,000 light-years from the galactic center. The arms contain both young, bright stars and older, more mature stars, along with nebulae, which are vast clouds of gas and dust that provide the raw material for future star formation. The central bulge of the Milky Way is densely packed with stars, some of which are among the oldest in the galaxy. At the heart of the bulge lies the supermassive black hole, Sagittarius A*, which has a mass of approximately 4 million times that of our Sun. Though invisible to telescopes that observe visible light, Sagittarius A* can be detected through its interaction with nearby matter, particularly the way it accelerates stars that pass close to it. The presence of this black hole suggests that it may have played a key role in the formation and evolution of the Milky Way itself, exerting a gravitational influence on the surrounding stars and matter. The halo of the Milky Way, which extends far beyond the disk, is populated by globular clusters, spherical collections of ancient stars. These stars are among the oldest known, and their orbits are not confined to the flat plane of the galaxy's disk but rather move in random directions around the galactic center. This suggests that the halo formed during the early stages of the galaxy's formation, before the disk fully developed. The halo also contains a significant amount of dark matter, an invisible substance that exerts a gravitational pull on the galaxy's visible matter, helping to keep it bound together despite the fast rotation of the spiral arms. Dark matter remains one of the greatest mysteries in astrophysics. Though we cannot see it, Its presence is inferred from the gravitational effects it has on the visible parts of the galaxy. Without dark matter, the stars in the Milky Way's outer regions would be moving too fast to remain gravitationally bound to the galaxy, and they would drift off into space. Instead, dark matter acts as a kind of cosmic glue, holding the galaxy together and influencing its structure and evolution. Estimates suggest that dark matter makes up about 85% of the total mass of the Milky Way, though its exact nature remains unknown. As we explore the Milky Way, we also learn about the processes that govern the lives of stars, planets, and other celestial objects. Stars are born from the collapse of gas clouds in the galaxy's spiral arms, where the density of gas is high enough to trigger the formation of new stars. These stars, like our Sun, generate energy through nuclear fusion, converting hydrogen into helium in their cores. Over time, stars evolve, burning through their nuclear fuel and eventually reaching the end of their lives. Smaller stars, like the Sun, will swell into red giants before shedding their outer layers and leaving behind a dense remnant known as a white dwarf. Larger stars may end their lives in spectacular supernova explosions, leaving behind neutron stars or black holes. The Milky Way is also home to an astonishing variety of planetary systems. As astronomers have discovered in recent decades, planets are incredibly common in our galaxy, with most stars hosting at least one planet. These planetary systems come in many different forms, ranging from rocky planets like Earth to gas giants like Jupiter and icy bodies similar to Neptune. Some planets orbit close to their stars, while others reside in the outer reaches of their systems. Among the thousands of exoplanets discovered so far, some have the potential to be habitable, with conditions that could support liquid water and potentially life. The question of life beyond Earth is one of the most profound mysteries we face as we explore the Milky Way. While life as we know it is limited to our home planet, the vastness of the galaxy suggests that the conditions for life could exist elsewhere. Many scientists believe that microbial life may be common in the universe, and that intelligent civilizations could be scattered throughout the galaxy. However, finding evidence of extraterrestrial life is a daunting task. Even with advanced telescopes and space probes, the distances between stars are immense, making direct exploration of other planetary systems incredibly challenging. Nonetheless, the search for life continues, as astronomers use sophisticated instruments to study the atmospheres of exoplanets and look for chemical signatures that could indicate the presence of life. Our own Sun, a middle-aged star, has orbited the center of the Milky Way many times during its 4.6 billion-year lifetime. As it moves through the galaxy, it experiences changing environments, from the relatively calm regions of the spiral arms to more turbulent areas near supernova remnants. These changing environments can have an impact on the solar system, as cosmic rays and other high-energy particles interact with the Sun and its planets. Despite these challenges, the Sun's stability and the protective magnetic field of the Earth have allowed life to flourish on our planet. The future of the Milky Way is as fascinating as its past. Like all galaxies, it is constantly evolving, and its ultimate fate is tied to the dynamics of the universe itself. The Milky Way is currently on a collision course with the nearby Andromeda Galaxy, the closest large galaxy to our own. In about 4 billion years, the two galaxies will begin to merge, creating a new, larger galaxy in the process. While this may seem like a cataclysmic event, the vast distances between stars mean that direct collisions between stars are unlikely. Instead, the gravitational interactions between the galaxies will reshape their structures, creating new star-forming regions and altering the orbits of stars within them. The Milky Way, then, is not a static object but a living, evolving entity, shaped by the forces of gravity, dark matter, and cosmic expansion. It is a place of incredible diversity, with stars in every stage of their life cycles, planetary systems of all kinds, and an ever-changing environment. As we continue to explore our galaxy, we are not only learning about the cosmos but also about our own origins. We are, after all, made of stardust. The elements that make up our bodies were forged in the hearts of stars that lived and died long before the Sun was born. In this sense, the Milky Way is not just our cosmic home but also the source of the matter that makes up everything we know. In the coming decades, New technologies will allow us to explore the Milky Way in even greater detail. Space telescopes, probes, and observatories will give us unprecedented views of the galaxy's stars, planets, and other objects. We may even discover new forms of life or unlock the secrets of dark matter. As we venture further into space, our understanding of the Milky Way will continue to grow, revealing new wonders and deepening our appreciation of the vast, interconnected universe we call home. The Milky Way is a symbol of the endless possibilities that lie beyond our small corner of the cosmos. It is a reminder of the incredible scale and beauty of the universe, and of our place within it. Whether we are observing the galaxy through a telescope, studying its stars and planets, or pondering the mysteries of dark matter and black holes, the Milky Way serves as a bridge between the known and the unknown. It stretches the limits of human curiosity and imagination, challenging us to explore, discover, and seek answers to some of the most profound questions ever posed. As we unravel its complexities, we begin to understand not only the physical universe but also the deeper philosophical and existential questions about where we come from and what our place in the cosmos might ultimately be. The vastness of the Milky Way reminds us just how small we are in the grand scheme of things. When we look at the night sky, we are peering across thousands, sometimes tens of thousands, of light years. Each tiny point of light could be a star with its own planetary system, perhaps harboring life or even intelligent civilizations. The immensity of our galaxy, combined with the incomprehensible number of other galaxies in the universe, suggests that the universe is filled with untold wonders and mysteries, waiting for us to discover them. Yet, for all its grandeur and size, the Milky Way is just one of countless galaxies, each with its own unique properties and history. The local group, the collection of galaxies to which the Milky Way belongs, includes around 54 galaxies, with the Milky Way and Andromeda being the two largest members. Beyond this, we find the Virgo supercluster, a massive grouping of galaxies that spans hundreds of millions of light years. And further still lies the Laniakea supercluster, a vast structure that encompasses our own galactic supercluster and others, stretching across more than 500 million light years. Despite being just one galaxy among billions, the Milky Way holds special significance for us. It is where humanity originated, where our solar system formed, and where we continue to thrive. The galaxy's spiral arms, swirling with star formation, and its central bulge, home to some of the oldest stars in existence, are our cosmic neighborhoods. As we explore our galaxy and learn more about its structure, its history, and its future, we are also exploring our own origins and the conditions that led to the development of life on Earth. This brings us to one of the most important questions in the study of the Milky Way and the universe at large. What are the conditions for life, and how common is it? While Earth remains the only known planet to host life, the discovery of thousands of exoplanets, planets orbiting other stars, has expanded our understanding of the potential for habitable environments in our galaxy. Some of these exoplanets reside in the so-called habitable zone, where conditions might be just right for liquid water to exist, which is thought to be essential for life as we know it. In recent years, the discovery of extremophiles, organisms that can survive in extreme environments on Earth, has further broadened our understanding of the conditions under which life can exist. These organisms thrive in places like deep-sea hydrothermal vents, acidic lakes, and even the vacuum of space, suggesting that life could arise in environments vastly different from those on Earth. This raises the possibility that life may be more widespread in the galaxy than previously thought, even if it is microbial in nature. The search for extraterrestrial life is closely tied to the study of the Milky Way, as our galaxy provides the best laboratory for understanding the processes that lead to the formation of planets, stars, and potentially life itself. By studying the chemistry of interstellar gas clouds, the formation of stars, and the conditions on distant exoplanets, scientists are piecing together the puzzle of how life might arise in different parts of the galaxy. The discovery of life beyond Earth, if it ever happens, would represent one of the most significant scientific breakthroughs in history, fundamentally altering our understanding of the universe and our place within it. As we search for life and explore the far reaches of our galaxy, we must also confront the challenges of space travel. The distances between stars in the Milky Way are immense, far beyond anything humanity has ever experienced. Traveling to even the nearest star, Proxima Centauri, would take over 4 years at the speed of light, and with current technology, it would take tens of thousands of years. This presents a monumental challenge for interstellar exploration, requiring new technologies and methods of propulsion that are still in the realm of theoretical physics. However, the desire to explore, to push the boundaries of what is possible, is deeply ingrained in human nature. Throughout history, humanity has ventured into the unknown, from crossing oceans to launching spacecraft to the moon and beyond. The exploration of the Milky Way represents the next frontier, one that will likely span generations. As we continue to develop our technological capabilities, it is possible that future missions will allow us to send probes to nearby stars, study distant planetary systems in detail, and perhaps even establish colonies on other worlds. In the meantime, we have a wealth of astronomical tools at our disposal to study the Milky Way from Earth. Radio telescopes, infrared observatories, and space-based instruments like the Hubble Space Telescope and the upcoming James Webb Space Telescope allow us to peer into the heart of our galaxy and observe its stars, nebulae, and black holes. These instruments provide invaluable data, helping scientists map the structure of the Milky Way, track the motion of stars, and understand the life cycles of celestial objects. One of the most fascinating aspects of the Milky Way is its ongoing interaction with neighboring galaxies. The Large and Small Magellanic Clouds, two irregular dwarf galaxies, are currently orbiting the Milky Way and are in the process of being absorbed by it. Over time, these galaxies will merge with the Milky Way, contributing their stars, gas, and dark matter to our galaxy's mass. These interactions provide insight into how galaxies grow and evolve over time, as larger galaxies like the Milky Way gradually incorporate smaller ones. Even more dramatic is the upcoming collision with the Andromeda Galaxy, which is currently hurtling toward the Milky Way at a speed of about 110 kilometers per second. In about 4 billion years, the two galaxies will begin to merge in a process that will take several billion years to complete. The result will be a new galaxy, often referred to as Milkomeda, with a shape and structure quite different from either of the original galaxies. While this may sound like a cataclysmic event, it is unlikely to have a significant impact on individual stars or planetary systems, as the distances between stars are so vast that direct collisions are rare. The merger with Andromeda is just one example of the larger cosmic dance that galaxies participate in as they move through the universe. Over time, galaxies interact, collide, and merge, constantly reshaping the cosmic landscape. These processes are driven by gravity, the fundamental force that governs the motion of objects in space. Gravity not only holds galaxies together but also causes them to cluster into groups and superclusters, forming the large-scale structure of the universe. At the heart of these interactions are the mysterious dark matter and dark energy, which make up the majority of the universe's mass and energy content. Dark matter, though invisible, exerts a gravitational pull on galaxies, helping to keep them bound together. Dark energy, on the other hand, is responsible for the accelerated expansion of the universe, driving galaxies apart on a cosmic scale. The interplay between these two forces shapes the evolution of galaxies like the Milky Way and determines the ultimate fate of the universe. As we study the Milky Way and its place in the universe, we are confronted with questions that extend beyond the realm of science and into the realm of philosophy. What is the nature of the universe? What is our place within it? Are we alone, or are there other intelligent civilizations out there, perhaps even within our own galaxy? These questions have captivated humanity for millennia, and while science has provided many answers, it has also raised new questions, deepening our sense of wonder and curiosity. The Milky Way, with its billions of stars, planets, and mysteries, is more than just a collection of celestial objects. It is a symbol of the vastness of the universe and the potential for discovery. Every star, every planet, every cloud of gas and dust tells a story about the history and future of our galaxy. As we continue to explore the Milky Way, we are not only learning about the cosmos but also about ourselves and our place in the grand tapestry of existence. The Milky Way is a reminder that we are part of something much larger than ourselves. We are inhabitants of a galaxy that has existed for billions of years and will continue to evolve long after we are gone. Our understanding of the Milky Way will continue to grow as we push the boundaries of exploration and discovery. And as we do, we will deepen our connection to the universe and to the mysteries that lie beyond. The journey to understand the Milky Way is a journey that has no end, a journey that will continue to inspire wonder, curiosity, and a sense of awe for generations to come. The more we learn about the Milky Way, the more it feels like a vast, living entity, teeming with processes that stretch across unimaginable spans of time. The stars that dot our night sky are not fixed. They are moving, shifting positions as they orbit the galactic center. Our own Sun, for instance, completes one full orbit around the center of the Milky Way roughly every 230 million years, a period known as a cosmic year or a galactic year. During this journey, it passes through different regions of the galaxy, including the spiral arms, where star formation is most active. This orbit around the galactic center ties into the larger history of our solar system. The Sun formed in a giant molecular cloud, a dense region of gas and dust that collapsed under gravity, leading to the birth of stars. Over billions of years, the Sun and its surrounding planets have traveled through different environments in the galaxy, sometimes experiencing intense radiation or passing by supernova remnants. These galactic influences could have played a role in shaping the evolution of life on Earth, particularly in the form of mass extinction events, such as the one that wiped out the dinosaurs 65 million years ago. At the center of the Milky Way lies one of its most enigmatic features, a supermassive black hole, known as Sagittarius A star. This black hole, with a mass of around 4 million times that of the Sun, exerts a powerful gravitational influence on the stars and gas around it. While we cannot observe the black hole directly, we can see its effects through the motion of nearby stars, which orbit the black hole at incredible speeds. Occasionally, material from a passing star or gas cloud gets too close to the black hole and is pulled in, creating a bright flare of radiation as the material is heated up and torn apart. Sagittarius A* is just one example of the many black holes that exist within our galaxy. Stellar mass black holes, which form when massive stars collapse at the end of their life cycles, are scattered throughout the Milky Way. These black holes are much smaller than Sagittarius A*, but still have a significant impact on their surroundings. They can form binary systems with companion stars, drawing material from the star and producing intense X-ray emissions. In some cases, black holes can merge with one another, releasing powerful gravitational waves that ripple through the fabric of spacetime. These gravitational waves were first directly detected in 2015 by the LIGO, Laser Interferometer Gravitational Wave Observatory, experiment, providing a new way to observe the universe. Unlike light, which can be blocked or scattered by dust and gas, gravitational waves pass through matter unimpeded, allowing us to probe regions of the galaxy that were previously hidden from view. The study of these waves opens up a new frontier in astrophysics, offering insights into the behavior of black holes, neutron stars, and other extreme objects in the Milky Way. But for all the attention given to black holes, they are just one part of the galaxy's story. The Milky Way is also home to a vast number of stars in various stages of their life cycles. Some stars, like our Sun, are in the stable, middle-aged phase of their evolution, fusing hydrogen into helium in their cores. Others, like red giants and white dwarfs, represent later stages of stellar evolution. Red giants are massive, swollen stars that have exhausted the hydrogen in their cores and are now burning heavier elements, while white dwarfs are the remnants of low-mass stars that have shed their outer layers and are slowly cooling over time. Then there are the most massive stars, which burn through their fuel quickly and end their lives in spectacular supernova explosions. These explosions are not only visually stunning but also play a crucial role in the galaxy's evolution. Supernovae release enormous amounts of energy and scatter heavy elements like iron, gold, and uranium into space, enriching the interstellar medium and providing the raw materials for future generations of stars and planets. Without supernovae, the elements necessary for life would not exist, making these explosions essential to the ongoing cycle of star formation in the galaxy. Interspersed between the stars are vast clouds of gas and dust, known as nebulae. These clouds serve as the nurseries for new stars, where gravity causes clumps of gas to collapse and ignite nuclear fusion in their cores. Nebulae come in many shapes and sizes, from the sprawling Orion Nebula to the intricate filaments of the Crab Nebula, a remnant of a supernova that was observed by Chinese astronomers in 1054 AD. Some nebulae glow brightly, illuminated by the stars forming within them, while others are dark and obscuring, blocking the light from background stars. The life cycle of stars, from their formation in nebulae to their deaths as supernovae or white dwarfs, is a continuous process that has been going on for billions of years and will continue for billions more. The Milky Way is a galaxy in motion, constantly evolving as stars are born, live out their lives, and eventually die, contributing to the ongoing recycling of material. This cycle of birth, death, and rebirth is not just a metaphor for the galaxy's existence, but a literal description of the processes that shape its structure and composition. Understanding the Milky Way's evolution also requires us to look at the role of dark matter, a mysterious substance that makes up about 85% of the total mass of the galaxy. Dark matter does not emit, absorb, or reflect light, making it invisible to telescopes, but its presence can be inferred from its gravitational effects on stars and galaxies. Without dark matter, the Milky Way and other galaxies would not have enough mass to hold themselves together, and the stars would fly apart. The nature of dark matter remains one of the biggest mysteries in modern astrophysics. Scientists have proposed various candidates for dark matter, including weakly interacting massive particles, WIMPs, and axions, but so far, no direct evidence for these particles has been found. Understanding dark matter is crucial for unlocking the secrets of the Milky Way's formation and structure, as it plays a fundamental role in shaping the galaxy's gravitational field and driving its rotation. In addition to dark matter, the Milky Way is also influenced by dark energy, the force responsible for the accelerated expansion of the universe. While dark energy does not have a direct impact on the structure of the galaxy itself, it plays a significant role in the larger cosmic environment in which the Milky Way exists. As the universe continues to expand, galaxies are being pushed farther apart, and over time, the Milky Way will become increasingly isolated from its neighboring galaxies. Despite these vast cosmic forces, the Milky Way remains a vibrant and dynamic place, filled with opportunities for exploration and discovery. New technologies, such as space-based observatories and advanced computer simulations, are allowing scientists to study the galaxy in unprecedented detail. These tools provide a window into the past, revealing the history of the Milky Way and offering clues about its future. One of the most exciting areas of research is the study of exoplanets, planets that orbit stars outside our solar system. Since the first exoplanet was discovered in 1992, thousands more have been found, ranging from gas giants like Jupiter to rocky, Earth-like planets. Some of these exoplanets reside in the habitable zone of their parent stars, where conditions may be suitable for liquid water and, potentially, life. The discovery of exoplanets has revolutionized our understanding of planetary systems and raised the tantalizing possibility that the Milky Way may be teeming with life. As we continue to explore the Milky Way and search for signs of life, we are also developing new ways to study the galaxy's most distant and elusive objects. The discovery of gravitational waves, for example, has opened a new window on the universe, allowing us to detect events like black hole mergers and neutron-star collisions. These signals provide a unique way to probe the invisible aspects of the Milky Way, offering insights into the fundamental forces that govern the cosmos. Looking ahead, the future of Milky Way exploration is filled with promise. New missions, such as the James Webb Space Telescope, the European Space Agency's Gaia mission, and NASA's upcoming Roman Space Telescope, will provide unprecedented views of the galaxy, helping to map its stars, track its evolution, and study its most mysterious phenomena. These missions will also continue the search for habitable planets and signs of extraterrestrial life, bringing us closer to answering one of the most profound questions in science: are we alone in the universe? As we stand on the cusp of this new era of exploration, it is important to remember that the Milky Way is not just a distant, abstract concept. It is our home, the galaxy that gave birth to the Sun, the Earth, and all the life that has ever existed. By studying the Milky Way, we are learning about ourselves, our origins, and our place in the cosmos. The more we understand our galaxy, the more we appreciate the delicate balance of forces that make life possible, and the incredible journey that has brought us to this point. The Milky Way is a vast, complex, and awe-inspiring galaxy, filled with mysteries that will continue to captivate humanity for generations to come. From its swirling spiral arms to its enigmatic black holes, from the birth of stars to the search for life, the Milky Way offers a window into the past, present, and future of the universe. As we continue to explore its depths, we will deepen our understanding of the cosmos and our place within it, forging a connection to the stars that will endure for as long as humanity continues to gaze up at the night sky in wonder. The Milky Way, in its sheer immensity, not only stretches across vast expanses of space but also stands as a testament to the intricate processes that define the universe. At its core, the galaxy is a balance of opposing forces: gravity, dark matter, and energy, creating a structure that has persisted for billions of years, evolving alongside the universe itself. Every star, planet, and cloud of gas plays its part in the grand dance of the Milky Way, moving in response to the galaxy's gravitational field and contributing to its ongoing life cycle. As we look deeper into the galaxy, we find that the Milky Way's story is not one of isolation but rather of interaction. Our galaxy, like many others, has collided and merged with smaller galaxies over time. These mergers have left traces, such as stellar streams, which are remnants of galaxies that were torn apart by the Milky Way's gravity. The Sagittarius dwarf galaxy is one such example, a smaller galaxy that is currently being consumed by the Milky Way, its stars gradually becoming part of our galaxy's halo. These mergers play a crucial role in the growth of galaxies, adding mass and sometimes triggering new waves of star formation. Beyond mergers, the Milky Way is part of a larger structure known as the Local Group, a collection of more than 50 galaxies bound together by gravity. The two largest members of the Local Group are the Milky Way and the Andromeda Galaxy, which is roughly the same size as the Milky Way and located about 2.5 million light-years away. The gravitational pull between the Milky Way and Andromeda is slowly bringing the two galaxies closer together, and in about 4.5 billion years, they will collide in a dramatic galactic merger. This event will reshape both galaxies, possibly forming a new elliptical galaxy, often referred to as Milkomeda. Though a galactic collision sounds catastrophic, it's important to note that the vast distances between stars mean that actual stellar collisions during such an event are extremely rare. Instead, the galaxy's stars will be thrown into new orbits, and regions of star formation may be triggered as gas clouds are compressed. The night sky, as seen from Earth, if our planet still exists at that time, would look very different, with Andromeda growing larger and eventually dominating the sky as the merger progresses. While the future merger with Andromeda is a monumental event, the Milky Way's present-day interactions with its satellite galaxies are also of significant interest. The Large and Small Magellanic Clouds, for instance, are two dwarf galaxies orbiting the Milky Way. These galaxies are slowly losing gas and stars to the Milky Way, forming structures like the Magellanic Stream, a long tail of gas stretching across the sky. The interactions between the Milky Way and these smaller galaxies are helping astronomers understand the complex gravitational relationships within the Local Group and the role of galactic cannibalism in the evolution of large galaxies. But the Milky Way's interactions are not limited to its neighbors. The galaxy is also influenced by cosmic phenomena on much larger scales, including the cosmic web, the vast, interconnected network of galaxies and galaxy clusters that make up the large-scale structure of the universe. The Milky Way is part of the Virgo supercluster, a massive concentration of galaxies that itself is part of an even larger structure known as the Laniakea supercluster. This web-like structure, with filaments of galaxies separated by vast voids, reflects the underlying distribution of dark matter, which exerts a gravitational pull on galaxies, shaping their motion and the overall architecture of the universe. As we peer deeper into the galaxy, we are constantly reminded of how interconnected everything is. The Milky Way is not a static entity but a dynamic, evolving system influenced by its past and present interactions with both nearby and distant objects. Our understanding of the galaxy is still evolving, as new discoveries are made using advanced technologies and space missions designed to explore its farthest reaches. One such mission, the Gaia Space Observatory, launched by the European Space Agency in 2013, is creating the most detailed map of the Milky Way ever made. By tracking the positions and movements of over 1 billion stars, Gaia is helping astronomers uncover the structure and dynamics of the galaxy in unprecedented detail. The data from Gaia is revealing previously unknown star clusters, improving our understanding of the galaxy's spiral arms, and providing insights into the distribution of dark matter within the Milky Way. It is also offering clues about the history of the galaxy, including the mergers and interactions that have shaped its evolution. Another exciting area of research is the search for the oldest stars in the Milky Way. These ancient stars, which formed shortly after the Big Bang, offer a glimpse into the early universe and the conditions that led to the formation of galaxies. By studying the chemical composition of these stars, astronomers can learn about the processes that created the first elements and how those elements were distributed throughout the galaxy. The discovery of these primordial stars is helping to piece together the puzzle of how the Milky Way and other galaxies like it came to be. While much of our attention is focused on the stars, planets, and gas clouds within the Milky Way, we should not forget about the mysteries that remain hidden in the vast dark spaces between them. Dark matter and dark energy, which together make up the majority of the universe's mass energy content, are still largely unknown. These forces influence the Milky Way in ways that we are only beginning to understand. Dark matter holds the galaxy together, providing the extra mass needed to explain the rotation curves of stars, while dark energy drives the expansion of the universe, gradually pushing galaxies apart. The nature of these dark components of the universe remains one of the greatest unsolved problems in modern physics. Understanding them will require not only new observations but also advancements in theoretical physics, possibly pointing us toward a new understanding of the fundamental forces that govern the cosmos. In the meantime, the Milky Way continues to serve as a laboratory for testing these ideas, as astronomers search for signs of dark matter particles or anomalies in the distribution of galaxies that might offer clues about dark energy. In this grand cosmic journey, the Milky Way stands as a symbol of the balance between the known and the unknown. It is a place where we can observe familiar processes, like the birth and death of stars, while also confronting the mysteries of dark matter, black holes, and the fate of the universe itself. As we continue to explore the galaxy, we will undoubtedly uncover new surprises, deepening our understanding of the cosmos and our place within it. Looking ahead, humanity's exploration of the Milky Way is likely to expand in ways we can scarcely imagine today. The future of space exploration may involve not just robotic probes and telescopes, but also human voyages to distant planets and stars. As we develop the technology to travel farther into space, we may one day leave our solar system and explore the farthest reaches of the Milky Way, seeking out new worlds and perhaps even new forms of life. The discovery of exoplanets in recent decades has already revolutionized our understanding of the potential for life beyond Earth. As our instruments become more sensitive, we are finding more and more planets in the habitable zones of their parent stars, regions where conditions may be right for liquid water, a key ingredient for life as we know it. The search for life in the Milky Way is one of the most exciting and profound endeavors in modern science, raising questions about what life might look like on other worlds and how it might differ from life on Earth. If we do find signs of life beyond our planet, it will not only change our understanding of the Milky Way but also our perception of ourselves and our place in the universe. The realization that we are not alone in the galaxy would be one of the most significant discoveries in human history, reshaping our sense of identity and our relationship with the cosmos. Even if we don't find life elsewhere in the Milky Way, the act of exploration itself will continue to inspire and challenge us. The more we learn about the galaxy, the more we appreciate the delicate balance of forces that has allowed life to flourish on Earth. This knowledge fosters a sense of awe and wonder at the complexity and beauty of the universe, as well as a sense of responsibility to preserve and protect our own planet within the vast expanse of the Milky Way. In the end, the Milky Way is more than just a galaxy. It is a reminder of the profound connection between all things. From the stars that light up the night sky to the planets that orbit them, From the black holes that shape the galaxy's structure to the dark matter that holds it together, the Milky Way is a tapestry of interconnected forces and processes, all working together to create the universe we inhabit. As we continue to explore this magnificent galaxy, we are not just learning about stars and planets. We are learning about ourselves and the universe that gave us life. The Milky Way is a testament to the power of science and human curiosity, a symbol of the infinite possibilities that lie ahead as we journey through the stars in search of knowledge, understanding, and perhaps even companionship among the stars. The journey through the Milky Way, both as observers and potential explorers, is not just a scientific pursuit, but also a deeply philosophical one. The more we learn about the galaxy, the more it prompts us to reflect on our origins, our future, and the very nature of existence. As we peer into the vastness of space, filled with billions of stars, each potentially home to its own planets and mysteries, we are forced to confront questions that have long fascinated humanity. Are we alone in the universe? What is the ultimate fate of the cosmos? How do we, as a species, fit into the grand tapestry of the Milky Way and beyond? As we continue to make strides in our understanding of the Milky Way, it's important to recognize that the galaxy itself is in constant motion. Over the course of millions and billions of years, the very structure of the Milky Way will change. Stars will be born and die, planetary systems will form and disintegrate, and the spiral arms themselves may shift or fade. Even our own solar system is on a journey through the galaxy, orbiting the galactic center at a speed of about 828,000 kilometers per hour, 514,000 miles per hour. Yet, even at this incredible speed, it takes roughly 230 million years for the Sun and its planets to complete a single orbit around the galaxy's core, a reminder of the immense scale and timescales at play in the Milky Way. This orbital journey is not without its hazards. As the solar system moves through different regions of the galaxy, it may pass through dense clouds of interstellar gas, star-forming regions, or even regions with higher concentrations of cosmic radiation. These interactions could have consequences for life on Earth, from triggering mass extinctions to influencing the climate. For instance, some scientists speculate that as the solar system moves through the spiral arms of the Milky Way, it may encounter conditions that could increase the likelihood of comet impacts on Earth. While these events are rare on human timescales, they are part of the dynamic and ever-changing nature of the galaxy. But the future of the Milky Way is not just about its internal evolution. It is also about its relationship with the wider universe. As mentioned earlier, the Milky Way is on a collision course with the Andromeda Galaxy, a dramatic event that will reshape both galaxies over the next few billion years. While this may seem like an unimaginably distant event, it is a reminder that galaxies, like stars and planets, are not static objects but are part of a larger cosmic dance, governed by the forces of gravity and the expansion of the universe. This collision will not be the end of the Milky Way, but rather the beginning of a new chapter in its story. The merger will likely trigger waves of star formation as gas clouds are compressed, and the combined galaxy will evolve into a new, larger structure. However, this new galaxy will exist in a universe that is also evolving. Over the next tens of billions of years, the expansion of the universe, driven by dark energy, will continue to accelerate, pushing distant galaxies farther and farther away. Eventually, galaxies beyond our local group will recede beyond the observable universe, leaving the Milky Way and its neighbors isolated in the vast cosmic void. As the universe continues to expand, the stars themselves will also change. The brightest, most massive stars will burn through their fuel quickly, exploding as supernovae and leaving behind neutron stars or black holes. The smaller, longer-lived stars, like red dwarfs, will continue to burn for trillions of years, slowly fading as they exhaust their nuclear fuel. In the distant future, the Milky Way may become a much dimmer, quieter place, with only faint, dying stars remaining. This long-term evolution, known as the stellar death of the universe, is a natural consequence of the finite lifespan of stars and the inexorable expansion of space. While these future scenarios are fascinating to contemplate, they also serve as a reminder of the transient nature of cosmic structures. The Milky Way, like all galaxies, is not eternal. It is a product of specific conditions in the universe, conditions that may not last forever. Understanding the life cycle of galaxies helps us appreciate the delicate balance of forces that allow structures like the Milky Way to exist, and it underscores the importance of studying them while we have the opportunity. In our quest to understand the Milky Way, we have only scratched the surface of what there is to learn. With each new discovery, from the mapping of dark matter to the detection of gravitational waves, we uncover new layers of complexity in the galaxy and the universe as a whole. The Milky Way serves as a microcosm of the broader universe, reflecting the fundamental processes that govern all of space and time. By studying our galaxy, we not only learn about its structure and history but also gain insights into the nature of galaxies in general and the laws of physics that shape them. In many ways, the study of the Milky Way is a bridge between the known and the unknown. It is a galaxy we can observe in detail, from the nearest stars to the most distant reaches of the galactic halo, yet it also contains mysteries that challenge our understanding of the cosmos. The search for dark matter, the investigation of black holes, and the quest to find life beyond Earth are all part of the larger effort to unravel the secrets of the Milky Way and, by extension, the universe itself. As we continue to explore the galaxy, both with our telescopes and, one day, with spacecraft capable of traveling to other star systems, we are reminded of the vast potential for discovery that lies ahead. The Milky Way, with its billions of stars and untold mysteries, is a reminder that we are still at the beginning of our journey as a spacefaring species. The more we learn about the galaxy, the more we realize how much there is left to explore. In the end, the Milky Way is more than just a collection of stars and gas. It is a symbol of the human drive to explore, to understand, and to seek out new knowledge. It is a reminder that we are part of something much larger than ourselves, connected to the cosmos in ways we are only beginning to comprehend. As we look up at the night sky, filled with the light of distant stars, we are reminded of our place in the galaxy and the vast possibilities that lie ahead as we continue to explore the wonders of the Milky Way and beyond. The story of the Milky Way is not just the story of a galaxy, it is the story of our cosmic home, the place where our solar system was born, where life on Earth emerged, and where humanity's future will unfold. It is a story that spans billions of years, encompassing the birth of stars, the formation of planets, and the ongoing dance of gravity and matter that shapes the galaxy. As we continue to study and explore the Milky Way, we will not only learn more about the galaxy itself but also about the broader universe and our place within it. The Milky Way is a galaxy rich with history, mystery, and potential. Its stars, planets, and black holes offer endless opportunities for discovery, while its past and future interactions with other galaxies remind us that the universe is a constantly evolving system. As we look to the future of space exploration, we can be certain that the Milky Way will remain a central focus of our efforts to understand the cosmos. Whether through the discovery of new exoplanets, the detection of dark matter, or the observation of distant black holes, the Milky Way will continue to captivate and inspire us as we seek to unlock the secrets of the universe and our place within it. In the vastness of the Milky Way, we find not just a galaxy of stars but a reflection of our own quest for knowledge, understanding, and meaning. As we continue to explore its depths, we are reminded that the journey through the stars is just beginning, and the wonders of the Milky Way will continue to inspire and challenge us for generations to come. As we continue to unravel the mysteries of the Milky Way, it is important to understand that this galaxy is far from being a static, unchanging object. It is a living system, constantly evolving over millions and billions of years. The very structure of the Milky Way, with its vast spiral arms, its dense central bulge, and its extended halo of stars and dark matter, is the product of countless cosmic events, collisions, star formations, supernovae explosions, and gravitational interactions. One of the most fascinating aspects of the Milky Way's evolution is the role of galactic mergers. Galaxies, like stars, often do not exist in isolation. Throughout their lifetimes, they interact with one another, sometimes passing by each other in fleeting encounters and sometimes merging together in massive, transformative collisions. The Milky Way itself has experienced several such mergers in the past, and it is likely to experience more in the future. These mergers play a crucial role in shaping the galaxy's structure, adding new stars, gas, and dark matter to its mass, while also triggering bursts of star formation as gas clouds are compressed by gravitational forces. Evidence of these past mergers can be seen in the Milky Way's stellar halo, a diffuse, spherical region of stars that surrounds the main disk of the galaxy. Some of these stars are thought to have originated in smaller galaxies that were consumed by the Milky Way long ago, their stars now scattered across the halo as the gravitational forces of the larger galaxy tore them apart. These ancient mergers have left behind streams of stars, remnants of the smaller galaxy's original structures, which can still be detected today using advanced telescopes. In fact, one of the most well-known examples of a galactic merger in progress is the Sagittarius dwarf galaxy. This small satellite galaxy is currently being consumed by the Milky Way, its stars being stretched and pulled into a long, looping stream as it orbits the larger galaxy. Over time, the Sagittarius dwarf galaxy will be completely absorbed into the Milky Way, its stars becoming part of the Milky Way's halo and disk. This ongoing interaction provides a glimpse into the dynamic processes that have shaped the Milky Way over billions of years and continue to do so today. But the story of galactic mergers is not just about smaller galaxies being absorbed by larger ones. In the future, the Milky Way itself is on a collision course with a galaxy much larger than any it has encountered before, the Andromeda Galaxy. Located about 2.5 million light-years away, Andromeda is the closest spiral galaxy to the Milky Way and is moving toward us at a speed of around 110 kilometers per second, 68 miles per second. While this may seem incredibly fast, the vast distance between the two galaxies means that the collision won't occur for another 4 to 5 billion years. When it does happen, the result will be a spectacular and dramatic event. The merger between the Milky Way and Andromeda, sometimes referred to as the Milkomeda event, will fundamentally alter the structure of both galaxies. As the two galaxies collide, their stars, gas, and dark matter will be thrown into disarray, with some stars being flung out into intergalactic space and others being pulled into new orbits around the merged galaxy's core. Despite the immense scale of the collision, the vast distances between stars mean that very few, if any, actual stellar collisions will occur. Instead, the stars will pass by one another, their orbits altered by the gravitational forces of the interacting galaxies. The gas within the two galaxies, however, will behave differently. As the galaxies merge, the gas clouds within them will collide and compress, triggering a burst of new star formation. This process will create thousands of new stars, lighting up the merged galaxy and giving it a new lease on life. Over time, the chaotic aftermath of the collision will settle, and the two galaxies will merge into a single, larger elliptical galaxy. This new galaxy will be very different from the spiral Milky Way we know today, with a more spherical shape and a less defined structure. But even as the Milky Way and Andromeda prepare for their distant collision, there are smaller satellite galaxies in our cosmic neighborhood that continue to interact with the Milky Way. One of the most famous examples is the Magellanic Clouds, two dwarf galaxies known as the Large Magellanic Cloud, LMC, and the Small Magellanic Cloud, SMC. These two galaxies are currently in orbit around the Milky Way and are slowly being drawn closer to it. In the distant future, they too will likely be absorbed by the Milky Way, adding their stars and gas to the galaxy's growing mass. Interestingly, recent studies suggest that the LMC and SMC may be interacting with the Milky Way in more complex ways than previously thought. The gravitational influence of these dwarf galaxies appears to be affecting the Milky Way's disk, potentially warping its structure and influencing the motion of stars within it. These interactions are a reminder that even relatively small galaxies can have a significant impact on the larger galaxies they orbit, and they provide valuable insights into the complex gravitational dynamics at play within the Milky Way. Another key aspect of the Milky Way's evolution is the ongoing cycle of star formation and death. Stars are born from vast clouds of gas and dust, known as molecular clouds, which are scattered throughout the galaxy's disk. When these clouds collapse under their own gravity, they form new stars, often in clusters. Over time, these stars evolve, with the most massive ones burning through their nuclear fuel quickly and ending their lives in dramatic supernova explosions. These explosions scatter heavy elements into space, enriching the interstellar medium and providing the raw materials for the next generation of stars. This process of stellar birth, death, and rebirth is a continuous cycle that has been ongoing for billions of years and will continue for billions more. However, it is not a process that can go on forever. As the galaxy's gas reserves are gradually depleted, the rate of star formation will eventually slow down. In the far future, the Milky Way may become a much quieter, dimmer place, with only faint, long-lived stars like red dwarfs remaining. These stars, which can burn for trillions of years, will be the final remnants of a once active galaxy. As we contemplate the future of the Milky Way, it's important to remember that the galaxy's fate is tied to the broader fate of the universe. The universe is currently expanding, driven by a mysterious force known as dark energy. This expansion is causing galaxies to move farther apart from one another, and it is expected to continue accelerating in the future. Over time, galaxies beyond our local group will recede beyond the observable universe, effectively disappearing from view. The Milky Way and its neighboring galaxies, including Andromeda, will be left isolated in a vast, empty universe. This future scenario, sometimes referred to as the Cosmic Dark Age, is a sobering reminder of the impermanence of cosmic structures. While the Milky Way and its stars will continue to exist for billions or even trillions of years, the universe around them will grow ever darker and emptier. Eventually, even the stars themselves will burn out, leaving behind only the faint glow of cooling white dwarfs, neutron stars, and black holes. But even in the distant future, long after the last stars have faded from view, the Milky Way will continue to hold mysteries and wonders that will inspire generations of explorers and scientists. The study of our galaxy is not just a scientific endeavor, it is a reflection of our deep desire to understand the cosmos and our place within it. As we continue to probe the depths of the Milky Way, we will undoubtedly uncover new surprises, new challenges, and new opportunities for discovery. The Milky Way, with its billions of stars and planets, its swirling clouds of gas and dust, and its hidden dark matter halo, is a reminder of the complexity and beauty of the universe. It is a galaxy that has been shaped by countless cosmic events, from the birth and death of stars to the gravitational pull of neighboring galaxies. It is a galaxy that holds the potential for new discoveries, from the search for extraterrestrial life to the investigation of dark matter and black holes. Ultimately, the Milky Way is more than just a collection of stars and planets. It is a symbol of the human spirit's quest for knowledge and understanding. It is a reminder that we are part of something much larger than ourselves, connected to the universe in ways we are only beginning to comprehend. As we continue to explore the galaxy, both with our telescopes and our imaginations, we are reminded that the journey through the stars is just beginning, and the Milky Way will continue to inspire and challenge us for generations to come. As we gaze deeper into the Milky Way, our understanding of its structure, evolution, and potential future continues to expand. The complexity of the galaxy is not only a testament to the power of cosmic forces, but also a mirror reflecting the immense scale and dynamics of the universe itself. There is an overwhelming sense of wonder when we consider that our entire solar system is just one tiny part of this grand galactic structure, moving through space as part of an intricate cosmic ballet. In the heart of this massive system lies the Milky Way's core, a region that plays a pivotal role in shaping the galaxy as a whole. This core, located around 27,000 light-years from Earth, is dominated by Sagittarius A*, a supermassive black hole with a mass approximately 4 million times that of the Sun. Sagittarius A** is surrounded by a dense cluster of stars, gas, and dust, all orbiting around the black hole at incredible speeds. The gravitational pull of this immense object is what helps to anchor the entire Milky Way, keeping it bound together despite the ongoing gravitational tug-of-war with other galaxies and the overall expansion of the universe. While supermassive black holes like Sagittarius A* are awe-inspiring objects in their own right, they also serve as key players in the life cycle of galaxies. It is believed that most large galaxies, including the Milky Way, have a supermassive black hole at their center, and these black holes can have profound effects on their surroundings. When material falls into the black hole, it can create intense bursts of radiation, which can influence star formation and regulate the flow of gas in the galaxy. These processes can shape the evolution of the galaxy over billions of years, creating feedback loops that determine how and where stars form within the galaxy's spiral arms and disk. The core of the Milky Way is also home to some of the oldest stars in the galaxy. These ancient stars, known as population II stars, are low in heavy elements compared to younger stars, indicating that they formed early in the galaxy's history, before the heavy elements created by supernovae had spread throughout the galaxy. Studying these stars provides valuable insights into the early stages of the Milky Way's formation, helping us to piece together the events that led to the galaxy's current structure. Moving outward from the galactic center, we encounter the iconic spiral arms that give the Milky Way its classic shape. These arms are not rigid structures but rather regions where stars, gas, and dust are concentrated in a winding pattern. The spiral arms are sites of intense star formation, as the density of gas and dust in these regions creates the perfect conditions for new stars to form. The bright, young stars that populate the spiral arms are responsible for much of the light we see when we observe the Milky Way from Earth, especially in the night sky during summer months, when the central bulge and nearby spiral arms are visible. The spiral arms themselves are shaped and maintained by a combination of gravitational forces, including the effects of dark matter. While the exact nature of dark matter remains one of the biggest unsolved mysteries in astrophysics, its presence is crucial for explaining the movement and structure of galaxies. In the Milky Way, dark matter is thought to form a vast halo around the galaxy, exerting gravitational forces that help to maintain the rotation of the galaxy and prevent it from flying apart. Without dark matter, the stars in the outer regions of the Milky Way would not be able to move as fast as they do without escaping the galaxy's gravitational pull. The Milky Way's spiral arms are also home to a vast array of planetary systems, including our own solar system. In recent years, the search for exoplanets, planets orbiting stars outside our solar system, has revealed that planets are far more common in the Milky Way than we once thought. To date, thousands of exoplanets have been discovered, and it is likely that billions more are waiting to be found. These planets come in a wide variety of types, from gas giants much larger than Jupiter to rocky planets similar to Earth. Some of these planets exist in the so-called habitable zone of their parent stars, where conditions might be suitable for liquid water to exist, a key ingredient for life as we know it. The discovery of exoplanets has profound implications for our understanding of the Milky Way and our place in the universe. For much of human history, we believe that the solar system was unique, but now we know that planetary systems are a common feature of the galaxy. This raises the tantalizing possibility that life could exist elsewhere in the Milky Way, on planets orbiting distant stars. The search for extraterrestrial life is one of the most exciting and challenging endeavors in modern science, and the discovery of even the simplest forms of life beyond Earth would be a groundbreaking achievement that would forever change our understanding of the universe and our place within it. As we continue our exploration of the Milky Way, both with telescopes and spacecraft, the question of life beyond Earth looms ever larger. The galaxy contains a staggering number of potential habitats for life, from planets in the habitable zones of stars to the icy moons of gas giants like Jupiter and Saturn. Missions like NASA's Kepler and TESS, Transiting Exoplanets Survey Satellite, have been instrumental in discovering exoplanets and identifying potential candidates for further study. At the same time, missions like the James Webb Space Telescope, which will peer deep into the atmospheres of exoplanets, hold the promise of detecting the chemical signatures of life. Yet, the search for life is not limited to exoplanets. Within our own solar system, there are several moons and dwarf planets that could potentially harbor life, particularly in their subsurface oceans. Europa, a moon of Jupiter, and Enceladus, a moon of Saturn, both have evidence of liquid water beneath their icy crusts, and both are considered prime candidates for future missions aimed at searching for signs of microbial life. If life is discovered within the Milky Way, whether on a distant exoplanet or within our own solar system, it would answer one of the most profound questions ever asked: are we alone? Beyond the search for life, the study of the Milky Way offers countless opportunities for discovery in a wide range of fields. From the study of star formation and the life cycles of stars to the investigation of cosmic phenomena like supernovae and black holes, The Milky Way is a vast laboratory where we can observe the forces and processes that shape the universe. It is a galaxy rich with diversity, filled with stars of all sizes and ages, planets of all types, and cosmic objects like pulsars, neutron stars, and quasars that continue to challenge our understanding of the laws of physics. One of the most exciting areas of research within the Milky Way is the study of gravitational waves, ripples in the fabric of spacetime caused by the acceleration of massive objects. First predicted by Albert Einstein's theory of general relativity, gravitational waves were finally detected directly in 2015 by the LIGO, Laser Interferometer Gravitational Wave Observatory, experiment. These waves provide a completely new way of observing the universe, allowing us to detect events that would otherwise be invisible, such as the collisions of black holes or neutron stars. As gravitational wave astronomy develops, it will provide us with unprecedented insights into the behavior of some of the most extreme objects in the Milky Way and beyond. The study of the Milky Way also extends to the exploration of its outer reaches, including its vast halo and the space between galaxies. While the Milky Way's disk is where most of its stars and visible matter are concentrated, the halo is a much larger and more diffuse region that extends far beyond the visible boundaries of the galaxy. This halo contains dark matter, as well as old stars and globular clusters, dense, spherical groups of stars that orbit the galactic center. By studying the halo, we can learn more about the distribution of dark matter in the galaxy and gain insights into the early stages of the Milky Way's formation. In recent years, the discovery of hypervelocity stars traveling at incredibly high speeds, has provided new clues about the dynamics of the Milky Way's halo. These stars are thought to have been ejected from the galactic center by interactions with Sagittarius A*, or by collisions with other stars. Their high velocities allow them to escape the gravitational pull of the Milky Way and travel into intergalactic space. Studying these stars not only helps us understand the forces at play within the galaxy but also offers a unique opportunity to probe the conditions of the galactic halo and the space beyond it. The Milky Way's relationship with other galaxies is another area of ongoing research. As part of the local group, the Milky Way is gravitationally bound to a collection of other galaxies, including Andromeda and several smaller satellite galaxies. These galaxies interact with one another, exchanging stars, gas, and dark matter, and their movements are shaped by the gravitational forces exerted by the dark matter halo that surrounds the group. By studying the interactions between the Milky Way and its neighbors, we can learn more about the behavior of galaxies and clusters and the role that dark matter plays in shaping these interactions. As we look to the future, the exploration of the Milky Way is set to enter a new era with the advent of advanced space telescopes, interstellar probes, and other technologies that will allow us to study the galaxy in greater detail than ever before. Missions like the upcoming Nancy Grace Roman Space Telescope and future gravitational wave detectors will provide us with new tools to explore the galaxy, from mapping its dark matter halo to searching for distant exoplanets and observing the most extreme objects in the cosmos. In the coming decades, humanity's understanding of the Milky Way will continue to deepen as we push the boundaries of technology and expand our reach into the cosmos. The Milky Way, with its billions of stars, planets, and mysteries, remains one of the most fascinating and important subjects of exploration for astronomers and scientists. Its secrets hold the key to understanding not only our own origins, but also the larger dynamics of the universe. Every new discovery within the Milky Way builds upon a foundation that stretches back centuries, as humanity has always been driven by the desire to comprehend its place in the cosmos. The future of our exploration of the Milky Way will likely involve more sophisticated methods of observing the galaxy. For instance, advancements in spectroscopy will enable us to analyze the composition of distant stars, nebulae, and exoplanet atmospheres in far greater detail. By doing so, we can improve our understanding of stellar life cycles, star formation processes, and the conditions required for planet habitability. With each new generation of telescopes, the sensitivity to faint and distant objects improves, allowing us to observe deeper into the galaxy and beyond. Moreover, the search for extraterrestrial intelligence, SETI, will continue to play a significant role in the study of the Milky Way. SETI efforts focus on detecting signals that could indicate the presence of intelligent civilizations elsewhere in the galaxy. With the ongoing development of more powerful radio telescopes, scientists hope to expand their search and potentially intercept any signals from distant civilizations. Although no definitive evidence of extraterrestrial life has been found yet, the vast number of stars and planetary systems in the Milky Way ensures that the search will persist for years to come. One of the most transformative missions humanity may embark on in the distant future is interstellar travel. While current spacecraft can only travel within our solar system, the idea of reaching nearby stars within the Milky Way is no longer purely science fiction. Concepts such as solar sails, which use the momentum of light to propel spacecraft, or even more exotic propulsion technologies like nuclear fusion drives or antimatter engines, may one day allow humans to journey beyond our solar system. Proposals like the Breakthrough Starshot initiative aim to develop tiny, lightweight spacecraft that could be propelled to nearby stars like Proxima Centauri at a fraction of the speed of light. Such missions would open a new chapter in the exploration of the Milky Way, enabling us to directly investigate other star systems and potentially uncover life elsewhere in the galaxy. These efforts, though still decades or even centuries away, are a testament to humanity's enduring desire to push the boundaries of what is possible and venture into the unknown. Another intriguing area of future research is the study of galactic collisions. While the Milky Way appears stable and serene from our vantage point, it is actually in the process of merging with other galaxies, both large and small. The most significant of these interactions will occur in about 4 billion years when the Milky Way is expected to collide with the Andromeda Galaxy. This event, often referred to as the Milkomeda merger, will dramatically reshape both galaxies, creating a new, larger galaxy over the course of billions of years. Despite the enormous scales and energies involved in such collisions, it is unlikely that individual stars will collide due to the vast distances between them. However, the merger will trigger a burst of star formation as gas clouds in both galaxies are compressed, leading to the birth of new stars. In the distant future, the night sky as seen from Earth, or whatever planet we may inhabit, will look dramatically different, as Andromeda draws closer and eventually merges with the Milky Way. The Milkomeda event will also have significant implications for the long-term future of our solar system. While it is impossible to predict exactly how the merger will affect the Sun and its planets, some simulations suggest that the solar system could be ejected from the new galaxy or thrown into a different orbit. Such events are a stark reminder of the dynamic and ever-changing nature of the Milky Way, and how even seemingly stable systems like our solar system are subject to the immense forces at play in the galaxy. Over the course of billions of years, the Milky Way will continue to evolve, shaped by both internal processes and interactions with its cosmic neighbors. Stellar life cycles will continue, with new stars being born from the remnants of older generations, and planetary systems forming around young stars. The balance between star formation and the death of stars will determine the overall brightness and structure of the galaxy, as older stars slowly fade away or end their lives in spectacular supernovae. In addition to these stellar processes, the distribution of dark matter in the Milky Way will continue to influence the galaxy's shape and rotation. Dark matter is believed to make up most of the galaxy's mass, but its exact nature remains elusive. Current research aims to detect dark matter particles through experiments on Earth and observations of cosmic phenomena, but so far, it has remained hidden. Nonetheless, understanding dark matter is essential for fully comprehending the Milky Way's behavior and its future evolution. Another major unknown that will likely come into sharper focus in the future is the role of cosmic rays, high-energy particles that travel through space at nearly the speed of light. These particles are thought to originate from sources such as supernovae, black holes, and neutron stars, and they permeate the galaxy, interacting with both stars and planetary systems. While cosmic rays have been detected for over a century, their precise origins and effects are still not fully understood. Research into these mysterious particles could provide new insights into the energetic processes that shape the galaxy. As our technological capabilities advance, we may also develop the ability to directly observe the supermassive black hole at the center of the Milky Way. Already, the Event Horizon Telescope has produced the first ever image of a black hole's event horizon, providing a glimpse into one of the most extreme environments in the universe. Future observations of Sagittarius A** could reveal how black holes influence the formation and evolution of galaxies, as well as provide new tests for Einstein's theory of general relativity. In the coming centuries, the study of the Milky Way will likely uncover even more profound mysteries and insights into the nature of the universe. The development of new technologies, such as gravitational wave detectors, advanced space telescopes, and interstellar probes, will allow us to explore the galaxy in ways that are currently unimaginable. Yet, even as we push the frontiers of knowledge, the Milky Way will continue to remind us of our small but significant place within the vast cosmic tapestry. Ultimately, the Milky Way is not just a collection of stars, planets, and cosmic phenomena. It is the home of humanity and countless other potential forms of life scattered across its billions of star systems. As we continue to explore and study the galaxy, we deepen our understanding of the forces that shaped our existence and the intricate web of connections that binds the cosmos together. The Milky Way, in all its complexity and beauty, remains one of the most awe-inspiring objects in the universe, a constant source of wonder and discovery for generations to come. The Milky Way is far more than the shining band of light that we see in the night sky. It is a vast, dynamic system filled with mystery, complexity, and potential for discovery. From the central supermassive black hole to the spiral arms where new stars are born, and from the dark matter that holds it all together to the billions of exoplanets that may harbor life, the Milky Way is a galaxy that challenges our understanding of the universe. Its study offers endless opportunities for exploration, promising to reveal new insights about the cosmos and our place within it for millennia to come. The story of the Milky Way is, in many ways, the story of humanity's quest to understand the universe, an ongoing journey into the depths of space and time. As we delve deeper into the mysteries of the Milky Way, we must consider the immense timescales on which galactic processes unfold. These timescales are far beyond the reach of human experience, yet they are fundamental to understanding the evolution of the galaxy and its ultimate fate. The stars we see today are only a fleeting moment in the Milky Way's 13.6 billion-year history. Over the next billions of years, the galaxy will undergo profound transformations as it continues to merge with smaller galaxies, form new stars, and reshape its structure. One of the most important processes in the galaxy's ongoing evolution is star formation. Stars are born from vast clouds of gas and dust, known as molecular clouds, which collapse under their own gravity. These clouds are scattered throughout the spiral arms of the Milky Way, forming regions of intense star formation called stellar nurseries. As new stars ignite and begin to shine, they inject energy into their surroundings, shaping the structure of the galaxy and influencing the formation of future generations of stars. In this way, star formation is a continuous cycle, with each new generation of stars contributing to the evolution of the galaxy as a whole. Star formation is also closely linked to the life cycles of stars. Massive stars, which burn through their fuel at a rapid pace, end their lives in violent supernova explosions. These explosions not only produce some of the heaviest elements in the universe but also send shockwaves through the surrounding interstellar medium, triggering the formation of new stars. The remnants of these supernovae, neutron stars and black holes, are scattered throughout the Milky Way, acting as cosmic markers of the galaxy's turbulent past. In contrast, smaller stars like our Sun live much longer, burning their fuel slowly over billions of years. Eventually, however, even these stars will reach the end of their lives, shedding their outer layers to form planetary nebulae, and leaving behind dense cores known as white dwarfs. Over time, the white dwarfs will cool and fade, becoming some of the dimmest objects in the galaxy. These stellar remnants, along with the black holes and neutron stars left behind by massive stars, form a kind of cosmic graveyard that tells the story of the galaxy's past. The interplay between star formation, stellar evolution, and the eventual death of stars has a profound impact on the overall structure of the Milky Way. Over time, the galaxy's spiral arms, which are currently filled with young, bright stars, will slowly fade as star formation rates decline. Eventually, the galaxy may transition into a more passive phase, where new stars are no longer formed in significant numbers. This process is already underway in other galaxies, and it is only a matter of time before the Milky Way follows suit. Despite these long-term changes, the Milky Way is far from a static or isolated system. The galaxy is surrounded by a population of smaller galaxies, known as satellite galaxies, which are gravitationally bound to it. Some of these satellites, such as the Large and Small Magellanic Clouds, are visible to the naked eye from Earth, while others are only detectable through telescopes. Over the course of billions of years, many of these satellite galaxies have been absorbed by the Milky Way, contributing to its growth and shaping its structure. In fact, some of the stars in the outer regions of the galaxy are thought to have originated in these smaller galaxies, providing evidence of past galactic mergers. One of the most significant of these mergers will occur when the Milky Way collides with the Andromeda Galaxy, our nearest large neighbor. This cosmic event, which is predicted to happen in about 4 billion years, will dramatically alter the structure of both galaxies. While the exact outcome of the merger is difficult to predict, simulations suggest that the two galaxies will merge to form a new, larger elliptical galaxy, sometimes referred to as Milkomeda. During the merger, stars and gas clouds will be thrown into new orbits, triggering bursts of star formation and potentially reshaping the entire structure of the new galaxy. The Milkomeda merger is just one example of the dynamic and interconnected nature of galaxies in the universe. On a larger scale, the Milky Way is part of a vast cosmic web of galaxies that are constantly interacting with one another. These interactions can take many forms, from gentle gravitational tugs to violent collisions, and they play a crucial role in shaping the evolution of the universe as a whole. As we continue to study the Milky Way and its neighbors, we gain new insights into the processes that govern the formation and evolution of galaxies across the cosmos. Another intriguing aspect of the Milky Way is its dark matter halo. Although dark matter cannot be directly observed, its presence is inferred from its gravitational effects on visible matter in the galaxy. The rotation curves of galaxies, including the Milky Way, reveal that the outer regions of the galaxy are rotating faster than they should be based on the amount of visible matter present. This discrepancy is explained by the presence of a vast halo of dark matter that surrounds the galaxy, providing the additional gravitational pull needed to account for the observed rotation speeds. Despite decades of research, the nature of dark matter remains one of the greatest unsolved mysteries in astrophysics. Scientists have proposed a number of candidates for dark matter particles, including weakly interacting massive particles, WIMPs, and axions, but so far, no direct evidence for these particles has been found. The discovery of dark matter particles would represent a major breakthrough in our understanding of the universe, shedding light on one of the most fundamental components of the Milky Way and other galaxies. In addition to dark matter, the Milky Way is also home to dark energy, the mysterious force driving the accelerated expansion of the universe. While dark energy is not confined to the Milky Way, its effects are felt throughout the galaxy, influencing the large-scale structure of the cosmos. Like dark matter, dark energy remains poorly understood, but it is thought to make up roughly 70% of the total energy density of the universe. Understanding the nature of dark energy is one of the major challenges facing cosmology in the 21st century. As we explore the Milky Way, we are not only learning about the galaxy itself but also about the broader universe in which it exists. The Milky Way is just one of billions of galaxies scattered across the cosmos, each with its own unique structure, history, and population of stars and planets. By studying our own galaxy in detail, we can develop a deeper understanding of the processes that govern the formation and evolution of galaxies throughout the universe. In the future, new technologies and missions will continue to expand our knowledge of the Milky Way. Space-based observatories, such as the James Webb Space Telescope, will provide unprecedented views of distant stars, galaxies, and exoplanets, helping us to answer some of the most fundamental questions about the universe. Meanwhile, the development of advanced propulsion technologies could one day allow us to send probes to other star systems within the Milky Way, providing direct observations of distant worlds and their potential for life. The exploration of the Milky Way is far from over, and the galaxy still holds many secrets waiting to be uncovered. From the search for extraterrestrial life to the study of dark matter and the nature of black holes, the Milky Way offers a wealth of opportunities for scientific discovery. As we continue to push the boundaries of our knowledge, the galaxy will remain a source of fascination and inspiration, reminding us of the vastness and complexity of the universe. In summary, the Milky Way Galaxy is an immense and intricate system that serves as a microcosm of the universe. Its spiral arms, filled with stars, gas, and dust, are the birthplace of new stars and planets, while its central black hole, Sagittarius A*, represents one of the most extreme environments in the cosmos. The galaxy's evolution is shaped by a combination of internal processes, such as star formation and supernova explosions, and external interactions with other galaxies, including the future collision with Andromeda. Additionally, the presence of dark matter and dark energy continues to challenge our understanding of the universe, driving ongoing research and exploration. The Milky Way is not only our home but also a window into the broader workings of the cosmos. As we continue to study its structure, history, and future, we gain valuable insights into the nature of galaxies, stars, and planetary systems, as well as the forces that shape the universe as a whole. The story of the Milky Way is far from complete, and the discoveries we make in the coming years will undoubtedly deepen our appreciation for the complexity and beauty of our galactic home. The story of the Milky Way is not merely a tale of stars and dust. It also encompasses the grand cosmic forces that have shaped its formation and evolution. Understanding these forces provides critical insights into the life cycle of galaxies and the nature of the universe itself. As we continue to explore the Milky Way, we uncover not just the details of our galactic home but also broader principles that govern cosmic phenomena. Galactic dynamics and structure. At the heart of the Milky Way lies a supermassive black hole known as Sagittarius A star. This black hole, with a mass of about 4 million times that of our Sun, exerts a profound influence on the galaxy's dynamics. The presence of Sagittarius A* is integral to the formation and maintenance of the galaxy's central bulge. The interactions between the black hole and the surrounding stars and gas clouds create complex gravitational interactions that shape the orbits of stars and contribute to the overall structure of the galaxy. The spiral arms of the Milky Way, which are rich in young, luminous stars, are thought to be influenced by density waves. These waves are disturbances in the galaxy's gravitational field that propagate through the galactic disk, compressing gas and dust and triggering the formation of new stars. As these density waves move through the disk, they create a pattern of star formation that gives rise to the galaxy's spiral structure. This mechanism is crucial in understanding why galaxies, including the Milky Way, exhibit distinct spiral patterns. Another significant feature of the Milky Way is its dark matter halo. This halo extends far beyond the visible edges of the galaxy and contains a substantial portion of the galaxy's mass. Dark matter, which does not emit or absorb light, interacts with visible matter through gravity. Its presence is inferred from the way galaxies rotate and the behavior of their stars and gas. The dark matter halo influences the galaxy's overall rotation curve, causing the outer regions of the Milky Way to rotate faster than expected based on the visible mass alone. The galactic halo and stellar populations. Beyond the main disk of the Milky Way lies the galactic halo, a vast, spherical region that contains older stars, globular clusters, and dark matter. The stars in the halo are typically older and more metal-poor than those in the disk, offering clues about the early stages of galactic formation. Globular clusters, which are dense collections of ancient stars, are scattered throughout the halo and are remnants of the Milky Way's early history. Studying these clusters provides valuable information about the conditions in the early galaxy and the processes that led to its formation. The halo also contains a diffuse population of stars and gas, known as the galactic corona. This region is less well studied due to its faintness and the difficulty of observing it from Earth. However, observations from space-based observatories and future missions are expected to shed light on the properties of the corona and its role in the galaxy's evolution. The Milky Way's interactions with its environment. The Milky Way's interactions with its environment are crucial to understanding its past and future. As a part of the local group, a collection of galaxies that includes Andromeda, M31, the Triangulum Galaxy, M33, and several smaller galaxies. The Milky Way is engaged in a dynamic cosmic dance with its neighbors. The gravitational influences of nearby galaxies affect the Milky Way's structure and star formation rates. In addition to its interactions with other galaxies, the Milky Way is also influenced by the vast cosmic web of dark matter and gas that permeates the universe. The galaxy's motion through the cosmic web affects its distribution of matter and its interactions with the intergalactic medium. Observations of the Milky Way's motion relative to the cosmic microwave background, a remnant of the Big Bang, provide insights into the galaxy's place in the larger cosmic structure. Future exploration and discoveries. The future of Milky Way exploration is set to be revolutionized by advancements in technology and observational techniques. Upcoming space missions, such as the European Space Agency's Gaia mission, aim to create a comprehensive three-dimensional map of the Milky Way, cataloging the positions, motions, and distances of billions of stars. This data will provide a detailed picture of the galaxy's structure and dynamics, offering new insights into its formation and evolution. The next generation of telescopes and observatories will also play a critical role in expanding our knowledge of the Milky Way. Instruments like the James Webb Space Telescope, JWST, are expected to revolutionize our understanding of star formation, exoplanets, and the early universe. By observing distant regions of the galaxy in unprecedented detail, these missions will enhance our understanding of the processes that shape the Milky Way. In addition to observational advances, theoretical and computational methods will continue to refine our understanding of galactic dynamics. Simulations of galactic evolution, which model the interactions of stars, gas, and dark matter, will help scientists predict the future behavior of the Milky Way and other galaxies. These models are essential for interpreting observational data and making predictions about the galaxy's long-term evolution. The search for life and habitability. One of the most exciting aspects of studying the Milky Way is the search for extraterrestrial life. The discovery of exoplanets, planets orbiting stars outside our solar system, has opened new possibilities for finding habitable worlds. The Milky Way contains billions of stars, many of which are likely to have planetary systems. Some of these planets may have conditions suitable for life, and future missions will focus on detecting and characterizing these worlds. The study of habitable zones, the regions around stars where conditions might be right for liquid water, will be a key area of research. Instruments like the Transiting Exoplanet Survey Satellite, TESS, and future space telescopes will continue to search for Earth-like planets in the habitable zones of their parent stars. Discovering such planets and analyzing their atmospheres could provide clues about the potential for life elsewhere in the galaxy. In addition to searching for habitable planets, researchers are also exploring the potential for life in extreme environments. Studies of extremophiles, organisms that thrive in extreme conditions on Earth, inform our understanding of how life might exist in harsh environments on other planets or moons. This research broadens the scope of the search for life and helps identify promising targets for future exploration. The Milky Way in the context of the universe. Understanding the Milky Way provides valuable context for studying the broader universe. The galaxy is a representative example of spiral galaxies, which make up a significant portion of the universe's galaxy population. By studying the Milky Way, scientists gain insights into the formation, structure, and evolution of spiral galaxies in general. Moreover, the Milky Way's interactions with other galaxies, such as its past and future collisions with the Andromeda Galaxy, offer clues about the dynamics of galactic mergers and the formation of larger cosmic structures. These interactions are a key aspect of galaxy evolution and play a role in shaping the distribution of galaxies in the universe. The philosophical and cultural impact. The study of the Milky Way also has philosophical and cultural implications. Understanding our place in the galaxy and the larger universe challenges our perceptions of existence and our role in the cosmos. The Milky Way has been a source of inspiration and wonder throughout human history, influencing art, literature, and scientific inquiry. As we continue to explore the galaxy, we are reminded of the vastness of the universe and the interconnectedness of all things. The quest to understand the Milky Way is part of a broader journey to comprehend the nature of reality and our place within it. This ongoing exploration reflects humanity's innate curiosity and desire to seek knowledge beyond our immediate surroundings. The Milky Way Galaxy is a vast, complex system that serves as a window into the broader workings of the universe. From its central supermassive black hole to its spiral arms and dark matter halo, the galaxy encompasses a wide range of phenomena that contribute to its overall structure and evolution. The ongoing exploration of the Milky Way offers valuable insights into the nature of galaxies, the forces that shape them, and the potential for life beyond our solar system. As technology and observational techniques continue to advance, our understanding of the Milky Way will deepen, revealing new mysteries and expanding our knowledge of the cosmos. The galaxy remains a source of fascination and inspiration, reminding us of the grandeur and complexity of the universe. The story of the Milky Way is far from over, and the discoveries made in the coming years will undoubtedly enrich our understanding of both our galactic home and the larger cosmic tapestry. The Milky Way's role in the cosmos extends beyond its own boundaries, intertwining with the grand narrative of galactic evolution. As we extend our gaze outward and contemplate the universe in its entirety, the Milky Way emerges as a vital component in understanding cosmic processes and structures. The galaxy's formation and growth provide a model for studying similar processes in other galaxies. Observations of distant galaxies reveal diverse morphologies and evolutionary stages, allowing scientists to compare and contrast these with the Milky Way. For example, we see elliptical galaxies, which differ significantly from spiral galaxies like ours, in their structure and star formation histories. The differences observed in these galaxies help us understand the range of outcomes that can arise from the same fundamental processes of galaxy formation and evolution. Simultaneously, the study of the Milky Way's past interactions with other galaxies offers a glimpse into the dynamic nature of galactic environments. The Milky Way's gravitational influence extends far beyond its visible disk, affecting nearby galaxies and intergalactic gas. These interactions are not isolated incidents but part of a larger cosmic web that connects galaxies across vast distances. Understanding these interactions helps us appreciate the complexity of galactic ecosystems and the interplay between gravitational forces, dark matter, and the intergalactic medium. One of the most compelling aspects of galactic dynamics is the concept of galactic cannibalism. This process involves larger galaxies, like the Milky Way, gradually merging with smaller galaxies, incorporating their stars, gas, and dark matter. Evidence of past mergers is visible in the Milky Way's structure, including the distribution of globular clusters and the presence of streams of stars that originated from smaller galaxies. The Milky Way's interaction with its satellite galaxies, such as the Magellanic Clouds, exemplifies this process on a smaller scale and provides valuable data for understanding the long-term effects of such mergers. Additionally, the Milky Way serves as a crucial benchmark for studying the distribution of matter in the universe. The galaxy's dark matter halo, which is far more extensive than its visible components, highlights the significance of dark matter in shaping cosmic structures. The rotation curve of the Milky Way, which shows higher than expected velocities in the outer regions, is a direct consequence of the dark matter halo's influence. By analyzing these rotation curves, scientists can infer the distribution of dark matter and apply these findings to other galaxies, offering a more comprehensive view of the universe's matter content. The search for understanding the Milky Way also intersects with the quest for extraterrestrial life. The presence of potentially habitable exoplanets in the Milky Way raises profound questions about the existence of life beyond Earth. The discovery of exoplanets in the habitable zones of their stars has broadened the scope of astrobiology, suggesting that Earth-like conditions might be more common than previously thought. Instruments such as the James Webb Space Telescope and future missions are expected to provide detailed observations of these exoplanets, including their atmospheric compositions and potential signs of life. In this pursuit, the Milky Way offers a laboratory for studying life's potential origins and evolution. The diverse environments within our galaxy, from the dense cores of star-forming regions to the cold outer reaches of the halo, present a range of conditions that could influence the development of life. By examining these environments and their potential to support life, scientists can develop hypotheses about the conditions necessary for life to thrive and apply these insights to the search for habitable worlds elsewhere in the universe. Furthermore, understanding the Milky Way contributes to our knowledge of cosmic events and phenomena, such as supernovae and gamma-ray bursts. These high-energy events play a critical role in the galaxy's life cycle by dispersing heavy elements into the interstellar medium and influencing star formation. Observing these events within the Milky Way provides essential data for understanding their origins, mechanisms, and impacts on galactic evolution. The Milky Way's interactions with the broader cosmic environment also provide insights into the nature of cosmic structures and the evolution of the universe. The galaxy's motion through the cosmic web, influenced by the distribution of dark matter and intergalactic gas, affects its interactions with neighboring galaxies and the large-scale structure of the universe. Studying these interactions helps scientists refine models of cosmic evolution and better understand the processes that shape the large-scale structure of the cosmos. As technology advances, our ability to observe and analyze the Milky Way continues to improve. Future missions and observatories will push the boundaries of our knowledge, revealing new aspects of the galaxy and its role in the universe. The development of more sensitive instruments, capable of detecting faint signals and resolving distant regions, will provide a more detailed and comprehensive view of the Milky Way. In addition to observational advancements, theoretical and computational models will play a crucial role in interpreting new data and making predictions about the galaxy's future. Simulations of galactic dynamics, star formation, and dark matter interactions will continue to evolve, offering new insights into the processes that govern the Milky Way and other galaxies. The exploration of the Milky Way is also a testament to human curiosity and ingenuity. The quest to understand our galaxy reflects a broader desire to comprehend the universe and our place within it. As we continue to explore the Milky Way and its surroundings, we contribute to a larger narrative of discovery and exploration that spans centuries and encompasses diverse scientific disciplines. The Milky Way Galaxy is a complex and dynamic system that plays a central role in our understanding of the universe. Its formation, structure, and evolution offer valuable insights into cosmic processes and the nature of galactic systems. As we explore the Milky Way and its interactions with the broader cosmos, we gain a deeper appreciation of the universe's complexity and the interconnectedness of all cosmic phenomena. The ongoing exploration of the Milky Way not only enhances our knowledge of our galactic home but also informs our understanding of the larger cosmic tapestry, driving future discoveries and inspiring new generations of scientists and explorers. The Milky Way's role in the grand scheme of the universe extends beyond its own structure and dynamics. It acts as a critical touchstone for many fundamental cosmic questions. As we delve deeper into its complexities, we encounter numerous phenomena that not only enhance our understanding of the galaxy but also contribute to our broader grasp of cosmic principles. Cosmic evolution and the Milky Way. The Milky Way is a living testament to the processes of cosmic evolution. Galaxies evolve through various stages, influenced by internal dynamics and external interactions. Our galaxy's journey from a primordial gas cloud to the sophisticated structure we see today involves a complex interplay of star formation, mergers, and accretion of intergalactic material. One key aspect of this evolutionary process is the galaxy's star formation history. The Milky Way began as a relatively featureless disk of gas and dust, with stars forming in clumps and gradually giving rise to a more organized structure. Observing different regions of the galaxy provides a snapshot of this evolutionary timeline. For example, the formation of star clusters and nebulae in the galaxy's spiral arms reveals ongoing processes of star birth, while older stellar populations in the halo and bulge represent earlier phases of galactic evolution. The Milky Way's interactions with neighboring galaxies also play a crucial role in its evolution. Past collisions and mergers have had significant impacts on its structure and composition. For instance, the Milky Way's history includes interactions with smaller galaxies that contributed to the formation of its halo and bulge. These interactions are not just historical footnotes, but integral to understanding the galaxy's current state and future trajectory. Galactic dynamics and cosmic structures. Understanding the Milky Way's dynamics provides insights into broader cosmic structures. The galaxy's gravitational field influences not only its own stars and gas but also the distribution of nearby galaxies. The Milky Way's motion through the cosmic web affects the arrangement and behavior of neighboring galaxies, contributing to the formation of larger structures like galaxy clusters and superclusters. The study of galactic dynamics also reveals the presence of dark matter, which affects the galaxy's rotation curve. Dark matter, an invisible substance that does not interact with light, exerts a gravitational influence that shapes the distribution of visible matter in the galaxy. This influence extends beyond the Milky Way, affecting the rotation and behavior of galaxies across the universe. By studying the Milky Way's dark matter halo, scientists gain insights into the distribution of dark matter in other galaxies and the overall structure of the cosmos. The role of the Milky Way in galactic research. The Milky Way serves as a natural laboratory for studying galactic phenomena. Its relatively close proximity allows for detailed observations and measurements that are not possible with more distant galaxies. This proximity is particularly valuable for studying the galaxy's central regions, where the effects of the supermassive black hole and interactions with surrounding stars and gas are most pronounced. Additionally, the Milky Way provides a reference for understanding other galaxies. By comparing the Milky Way with other spiral galaxies, astronomers can identify common features and differences, refining models of galaxy formation and evolution. This comparative approach helps scientists understand the range of galactic structures and behaviors, providing a broader context for studying the universe. Future exploration and technological advancements. The future of Milky Way exploration is bright, with upcoming missions and technological advancements poised to enhance our understanding of the galaxy. Space telescopes like the James Webb Space Telescope, JWST, and the upcoming Extremely Large Telescope, ELT, will offer unprecedented views of the galaxy, allowing scientists to probe its structure and dynamics with greater precision. The Gaia mission, which has already provided a detailed three-dimensional map of the Milky Way, will continue to refine our knowledge of the galaxy's star populations and their motions. The data from Gaia and future missions will contribute to a more comprehensive understanding of the Milky Way's formation, evolution, and structure. Implications for astrobiology and the search for life. The Milky Way's potential for hosting habitable planets and extraterrestrial life has significant implications for astrobiology. The discovery of exoplanets within the habitable zones of their stars suggests that Earth-like conditions might be common throughout the galaxy. This realization has profound implications for our search for life beyond Earth. The study of habitable environments within the Milky Way helps scientists identify promising targets for future exploration. Missions aimed at detecting biosignatures, indicators of life, in the atmospheres of exoplanets will provide critical information about the potential for life elsewhere in the galaxy. The search for extraterrestrial intelligence, SETI, also benefits from our understanding of the Milky Way, as it focuses on detecting signals from advanced civilizations within our galactic neighborhood. The Milky Way and cosmic philosophy. The study of the Milky Way also raises philosophical questions about humanity's place in the universe. Our exploration of the galaxy challenges our perceptions of existence and our relationship with the cosmos. The vastness of the Milky Way and the complexity of its structure prompt reflections on our significance and the nature of life itself. The Milky Way's grandeur and scale inspire a sense of wonder and curiosity that drives scientific inquiry and exploration. As we continue to investigate its mysteries, we gain not only knowledge but also a deeper appreciation for the interconnectedness of all things in the universe. This sense of wonder fuels our desire to understand the cosmos and our place within it, motivating future generations of scientists and explorers. The Milky Way Galaxy is a cornerstone of cosmic research and exploration. Its complex structure, dynamic interactions, and role in the broader universe provide invaluable insights into the nature of galaxies, dark matter, and the potential for life beyond Earth. As technology advances and observational capabilities improve, our understanding of the Milky Way will continue to evolve, revealing new aspects of its formation, evolution, and place in the cosmos. The study of the Milky Way is not only about understanding our galactic home but also about gaining a deeper appreciation for the universe and our place within it. The ongoing exploration of the Milky Way reflects humanity's enduring curiosity and quest for knowledge, driving discoveries that expand our understanding of the cosmos and inspire new frontiers of exploration. As we continue to uncover the mysteries of the Milky Way, we contribute to a grand narrative of cosmic discovery that spans both time and space, enriching our understanding of the universe and our place in it. The Milky Way Galaxy, our cosmic home, is not just an isolated entity but a fundamental piece of the larger cosmic puzzle. Its study provides insights into the formation, evolution, and behavior of galaxies across the universe. By examining the Milky Way, we gain a deeper understanding of galactic processes that can be applied to other galaxies, enhancing our knowledge of the cosmos as a whole. As we delve into the Milky Way's structure, it's essential to appreciate the interplay between its various components. The galaxy's disk, bulge, and halo are interconnected in ways that influence the galaxy's overall dynamics and evolution. The disk, with its spiral arms, is where most of the galaxy's star formation occurs. This region is rich in gas and dust, providing the raw materials for new stars and planetary systems. The spiral arms themselves are thought to be regions of higher density within the galactic disk, shaped by gravitational interactions and density waves that propagate through the galaxy. The bulge, a dense concentration of older stars located at the center of the Milky Way, provides a contrasting environment to the disk. This region is characterized by its high stellar density and complex dynamics, influenced by the presence of the supermassive black hole, Sagittarius A star. The interaction between the black hole and the surrounding stars and gas creates a dynamic environment that shapes the bulge's structure and the orbits of its stars. The halo, extending far beyond the visible edges of the galaxy, contains some of the oldest stars and globular clusters. These ancient structures are remnants of the early galaxy and offer clues about its formation. The halo also houses a significant amount of dark matter, an invisible substance that exerts gravitational influence and affects the rotation curve of the Milky Way. The dark matter halo's presence is crucial for understanding the galaxy's total mass and the distribution of matter within it. Exploring the Milky Way's interactions with other galaxies provides further insights into its evolution. The Milky Way is part of the Local Group, a collection of galaxies that includes the Andromeda Galaxy, the Triangulum Galaxy, and several smaller galaxies. The gravitational interactions within this group influence the Milky Way's structure and dynamics. For example, the Milky Way's interactions with the Magellanic Clouds, two small galaxies orbiting our own, have led to the creation of tidal streams of stars and gas that provide valuable information about the galaxy's history. The study of these interactions extends to the Milky Way's past and future encounters with other galaxies. One of the most significant future events is the predicted collision with the Andromeda Galaxy. This collision, expected to occur in about 4 billion years, will reshape both galaxies and lead to the formation of a new, larger galaxy. Observing and modeling these interactions helps scientists understand the processes involved in galaxy mergers and the resulting changes in galactic structure. Beyond galactic interactions, the Milky Way's place within the larger cosmic web offers valuable insights into the structure and evolution of the universe. The galaxy is part of a vast network of interconnected cosmic structures, including filaments of dark matter and gas that form a complex web spanning billions of light years. Understanding the Milky Way's position within this web helps scientists study the distribution of matter on the largest scales and the formation of cosmic structures. The Milky Way's study also intersects with the field of astrobiology. The discovery of exoplanets within the galaxy, particularly those in the habitable zones of their stars, has profound implications for the search for extraterrestrial life. By studying these planets and their environments, scientists can identify potentially habitable worlds and investigate the conditions necessary for life. The search for biosignatures and technosignatures, indicators of life or advanced civilizations, will continue to drive research and exploration in the coming years. In addition to the search for life, The Milky Way serves as a natural laboratory for studying fundamental cosmic processes. Observations of supernovae, gamma-ray bursts, and other high-energy phenomena within the galaxy provide critical information about stellar evolution, the synthesis of heavy elements, and the dynamics of cosmic explosions. These observations contribute to our understanding of the life cycles of stars and the impacts of these events on the surrounding galaxy. The Milky Way's exploration is further enriched by advancements in technology and observational techniques. Space missions such as the Gaia spacecraft, which maps the positions and motions of stars, and the upcoming James Webb Space Telescope, designed to observe distant regions of the galaxy, promise to revolutionize our understanding of the Milky Way. These tools enable scientists to probe the galaxy's structure and dynamics with unprecedented precision, uncovering new details about its formation and evolution. As we continue to explore the Milky Way, we also gain insights into the broader nature of the universe. The galaxy serves as a benchmark for studying other galaxies and cosmic phenomena, providing a reference point for understanding galactic evolution and the distribution of matter. By comparing the Milky Way with other galaxies, scientists can refine models of galaxy formation and evolution, enhancing our understanding of the universe's history and structure. In summary, the Milky Way Galaxy is a crucial piece of the cosmic puzzle, offering valuable insights into the formation, structure, and evolution of galaxies. Its study provides a foundation for understanding broader cosmic processes and contributes to our knowledge of the universe. As technology advances and observational techniques improve, our understanding of the Milky Way will continue to evolve, revealing new aspects of its complexity and enhancing our grasp of the cosmos. The ongoing exploration of the Milky Way reflects humanity's enduring curiosity and quest for knowledge, driving discoveries that expand our understanding of the universe and inspire future generations of scientists and explorers. The Milky Way, as one of the most studied and best understood galaxies, serves as a vital touchstone for many fundamental concepts in astronomy and astrophysics. Our exploration of this galaxy reveals much about the nature of galaxies in general and the universe's broader structure. As we delve deeper into its mysteries, we gain insights that extend beyond the Milky Way and contribute to our understanding of cosmic phenomena on a universal scale. Central to the study of the Milky Way is its role as a laboratory for investigating galactic formation and evolution. The galaxy's diverse components, its stellar populations, interstellar medium, and dark matter halo, interact in complex ways that shape its structure and behavior. Observations of the Milky Way's spiral arms, for instance, provide clues about the processes driving star formation and the dynamics of galactic disks. The interaction between the galaxy's gas and stars in these arms reveals how density waves can trigger bursts of star formation, creating the characteristic patterns we observe. The galaxy's central bulge, with its dense concentration of stars, offers insights into the processes that govern the formation of galactic cores. The presence of a supermassive black hole at the center of the Milky Way influences the dynamics of the bulge and the surrounding stars. Studying the orbits of stars near this black hole helps astronomers understand its mass and gravitational influence, providing valuable information about the role of supermassive black holes in galaxy formation and evolution. The Milky Way's halo, extending far beyond the visible disk, contains some of the galaxy's oldest stars and globular clusters. These ancient structures are remnants of the early universe and provide a window into the conditions that prevailed during the galaxy's formative years. By studying these halo stars and clusters, astronomers can trace the galaxy's history and the processes that shaped its current structure. One of the most intriguing aspects of the Milky Way's halo is the presence of dark matter. Dark matter, an invisible substance that does not emit or absorb light, exerts a significant gravitational influence on the galaxy. The rotation curve of the Milky Way, which shows higher velocities in the outer regions than expected based on visible matter alone, is a direct consequence of the dark matter halo. This discovery has profound implications for our understanding of galaxy dynamics and the distribution of matter in the universe. The Milky Way's interactions with neighboring galaxies also offer valuable insights into galactic processes. The Local Group, a collection of galaxies that includes the Milky Way, Andromeda, and several smaller galaxies, provides a natural laboratory for studying galactic interactions and mergers. Observations of these interactions reveal how galaxies influence each other's structure and evolution. For example, the Milky Way's interactions with the Magellanic Clouds, two small galaxies orbiting it, have led to the creation of tidal streams of stars and gas that provide clues about the galaxy's history. Looking further afield, the Milky Way's interactions with other galaxies in the local group and beyond offer insights into the broader cosmic environment. The galaxy's motion through the cosmic web, a vast network of interconnected structures, affects its interactions with neighboring galaxies and the distribution of matter on large scales. Understanding these interactions helps scientists study the formation and evolution of cosmic structures, including galaxy clusters and superclusters. The Milky Way also plays a crucial role in the search for extraterrestrial life. The discovery of exoplanets within the galaxy, particularly those located in the habitable zones of their stars, has significant implications for astrobiology. By studying these planets and their potential to support life, scientists can identify promising targets for future exploration. The study of exoplanets, combined with the search for biosignatures and technosignatures, drives research into the potential for life beyond Earth. Technological advancements continue to enhance our exploration of the Milky Way. The Gaia spacecraft, for example, has provided a detailed three-dimensional map of the galaxy, offering insights into the positions and motions of stars. This data is crucial for understanding the structure and dynamics of the Milky Way. Similarly, the James Webb Space Telescope, with its advanced observational capabilities, is expected to revolutionize our understanding of the galaxy by providing new details about its formation and evolution. The study of the Milky Way is also intertwined with broader cosmic questions, such as the nature of dark energy and the expansion of the universe. By understanding the Milky Way's structure and dynamics, scientists can refine models of cosmic expansion and the distribution of dark energy. This research contributes to our understanding of the universe's overall behavior and the forces that govern its evolution. In addition to its scientific significance, the Milky Way holds a special place in human culture and imagination. Its presence in the night sky has inspired countless myths, legends, and artistic works throughout history. The galaxy's grandeur and complexity continue to captivate the human spirit, driving our quest for knowledge and exploration. As we continue to explore the Milky Way, we are not only uncovering the secrets of our galactic home but also contributing to a broader understanding of the universe. The galaxy serves as a key piece of the cosmic puzzle, offering insights into the formation and evolution of galaxies, the distribution of matter, and the potential for life beyond Earth. The ongoing study of the Milky Way reflects humanity's enduring curiosity and quest for knowledge, inspiring new discoveries and expanding our understanding of the cosmos. The Milky Way Galaxy is a complex and dynamic system that plays a central role in our understanding of the universe. Its structure, evolution, and interactions with other galaxies provide valuable insights into fundamental cosmic processes. As technology advances and our observational capabilities improve, our knowledge of the Milky Way will continue to evolve, revealing new aspects of its complexity and contributing to a deeper understanding of the universe. The exploration of the Milky Way reflects our fascination with the cosmos and our desire to uncover the mysteries of the universe, driving scientific discovery and inspiring future generations of explorers. As we continue to explore the Milky Way, its rich and complex nature becomes increasingly apparent. Our journey through this galaxy reveals not only its individual components but also its role within the broader cosmic framework. The Milky Way, with its intricate structure and dynamic processes, serves as a fundamental reference point for understanding galactic and cosmic phenomena. One of the most captivating aspects of the Milky Way is its role as a dynamic and evolving system. The galaxy is not static but is continually changing through various processes. Star formation, for instance, is an ongoing process that shapes the galaxy's structure. Massive clouds of gas and dust, known as molecular clouds, serve as the birthplaces of new stars. The intricate dance of these clouds, influenced by gravity and other forces, leads to the formation of stars and planetary systems. Over time, These newly formed stars contribute to the galaxy's evolution by enriching the interstellar medium with heavier elements through processes like supernova explosions. The interplay between star formation and the galaxy's overall dynamics is a key area of research. The Milky Way's spiral arms, for example, are regions of heightened star formation activity. These arms are thought to be the result of density waves, oscillations in the galaxy's disk that propagate outward, triggering the formation of new stars and creating the characteristic spiral pattern. The study of these density waves and their effects on star formation provides insights into the mechanisms driving the galaxy's spiral structure. In addition to star formation, the Milky Way's structure is influenced by its gravitational interactions with other galaxies and cosmic structures. The galaxy is part of a larger cosmic web, a network of interconnected filaments of dark matter and gas that spans the universe. The Milky Way's position within this web affects its interactions with neighboring galaxies and its overall evolution. Observations of these interactions help scientists understand the processes involved in galaxy formation and the distribution of matter on the largest scales. The Milky Way's interaction with its satellite galaxies, such as the Magellanic Clouds, offers valuable insights into the galaxy's history and dynamics. These interactions have led to the formation of tidal streams, a phenomenon where stars and gas are pulled out of their parent galaxies and distributed across the Milky Way. Studying these tidal streams helps astronomers trace the Milky Way's past interactions and understand the processes that have shaped its current structure. Another significant aspect of the Milky Way is its dark matter halo. Dark matter, which does not emit or absorb light, exerts a gravitational influence on the galaxy and affects its rotation curve. The presence of dark matter in the halo helps explain why the Milky Way's outer regions rotate faster than expected based on visible matter alone. This discovery has profound implications for our understanding of galactic dynamics and the distribution of matter in the universe. Research into dark matter also extends to its role in the formation of galaxies and cosmic structures. The Milky Way's central supermassive black hole, known as Sagittarius A*, is another area of intense research. This black hole, with a mass of about 4 million times that of the Sun, exerts a significant gravitational influence on the surrounding stars and gas. Observations of the stars orbiting near Sagittarius A* provide crucial information about the black hole's mass and the dynamics of the galaxy's core. Understanding the role of supermassive black holes in galactic evolution helps scientists explore the relationship between black holes and galaxy formation. The study of the Milky Way also has implications for our understanding of cosmic evolution. The galaxy serves as a natural laboratory for examining processes that occur in other galaxies. By comparing the Milky Way with other galaxies, astronomers can identify common features and differences, refining models of galaxy formation and evolution. This comparative approach helps scientists understand the range of galactic structures and behaviors and provides a broader context for studying the universe. Technological advancements continue to enhance our exploration of the Milky Way. Space missions such as the Gaia spacecraft have revolutionized our understanding of the galaxy by providing detailed maps of stellar positions and motions. This data allows scientists to study the galaxy's structure and dynamics with unprecedented precision. The upcoming James Webb Space Telescope, with its advanced observational capabilities, is expected to further expand our knowledge of the Milky Way by providing new insights into its formation and evolution. The Milky Way's role in the search for extraterrestrial life is another exciting area of research. The discovery of exoplanets within the galaxy, particularly those located in the habitable zones of their stars, has significant implications for astrobiology. By studying these planets and their potential to support life, scientists can identify promising targets for future exploration. The search for biosignatures, indicators of life, in the atmospheres of exoplanets, and the search for technosignatures, signals from advanced civilizations, are key areas of research that are informed by our understanding of the Milky Way. The Milky Way's study is also closely linked to broader cosmic questions, such as the nature of dark energy and the expansion of the universe. By understanding the Milky Way's structure and dynamics, scientists can refine models of cosmic expansion and the distribution of dark energy. This research contributes to our understanding of the universe's overall behavior and the forces that govern its evolution. In addition to its scientific significance, the Milky Way holds a special place in human culture and imagination. Its presence in the night sky has inspired countless myths, legends, and artistic works throughout history. The galaxy's grandeur and complexity continue to captivate the human spirit, driving our quest for knowledge and exploration. As we continue to explore the Milky Way, we are not only uncovering the secrets of our galactic home but also contributing to a broader understanding of the universe. The galaxy serves as a key piece of the cosmic puzzle, offering insights into the formation and evolution of galaxies, the distribution of matter, and the potential for life beyond Earth. The ongoing study of the Milky Way reflects humanity's enduring curiosity and quest for knowledge, inspiring new discoveries and expanding our understanding of the cosmos. The Milky Way's exploration is a testament to our ability to unravel the mysteries of the universe. Through advancements in technology and observational techniques, we continue to gain new insights into the galaxy's structure and dynamics. Each discovery adds to our understanding of the Milky Way and its place in the cosmos, enriching our knowledge of the universe and our place within it. As we look to the future, the exploration of the Milky Way will continue to drive scientific inquiry and inspire future generations of explorers, fueling our curiosity and expanding our horizons. The Milky Way Galaxy, as an expansive and intricate system, continues to captivate and challenge scientists, offering endless opportunities for discovery and exploration. Its sheer scale and complexity invite us to investigate not only its visible components but also the elusive and less understood aspects, such as dark matter and dark energy, which play crucial roles in shaping the galaxy's structure and evolution. Central to understanding the Milky Way is the concept of galactic rotation. The galaxy's rotation curve, which plots the rotational velocity of stars and gas against their distance from the galactic center, reveals much about the distribution of mass within the Milky Way. Observations show that the rotational speeds of stars and gas remain high even at large distances from the center, indicating the presence of a significant amount of unseen mass, primarily dark matter. This finding has profound implications for our understanding of the galaxy's mass distribution and the nature of dark matter itself. As we delve deeper into the Milky Way's structure, it's essential to consider its role within the broader cosmic landscape. The Milky Way is part of a larger structure known as the Local Group, a collection of galaxies that includes our neighboring Andromeda Galaxy and several smaller galaxies. The gravitational interactions between these galaxies influence their structure and evolution, providing insights into the dynamics of galactic clusters and superclusters. The Milky Way's interactions with these neighboring galaxies, such as the Andromeda Galaxy and the Magellanic Clouds, offer valuable clues about the processes that govern galaxy mergers and the formation of new galactic structures. One of the most fascinating aspects of the Milky Way is its stellar populations. The galaxy hosts a diverse array of stars, ranging from young, massive stars in the spiral arms to older, cooler stars in the halo and bulge. The study of these different populations provides insights into the galaxy's formation history and the processes that have shaped its current structure. For example, the presence of ancient stars in the halo suggests that the Milky Way formed through the gradual accumulation of material over billions of years. These ancient stars, along with globular clusters and other relics from the early galaxy, serve as witnesses to the Milky Way's formative years and offer a glimpse into the early universe. The interstellar medium, ISM, is another critical component of the Milky Way. The ISM, composed of gas and dust, plays a crucial role in the galaxy's ecology. It serves as the reservoir from which new stars and planetary systems are formed. The ISM is also the site of various dynamic processes, such as supernova explosions and stellar winds, which influence the galaxy's structure and evolution. Observations of the ISM provide valuable information about the distribution of gas and dust, the processes of star formation, and the interactions between different components of the galaxy. Recent advancements in observational technology have significantly enhanced our understanding of the Milky Way. Space-based telescopes, such as the Hubble Space Telescope and the upcoming James Webb Space Telescope, offer unprecedented views of the galaxy in various wavelengths of light. These observations reveal intricate details about the galaxy's structure, such as the distribution of stars and gas, the formation of new star clusters, and the interactions between different components. The Gaia spacecraft, in particular, has revolutionized our understanding of the Milky Way by providing precise measurements of stellar positions and motions. This data has enabled scientists to map the galaxy's structure with remarkable accuracy and gain insights into its dynamic processes. In addition to these technological advancements, the study of the Milky Way is also informed by theoretical models and simulations. Computational models that simulate the formation and evolution of galaxies help scientists understand the complex processes that shape the Milky Way. These models incorporate various physical processes, such as gravity, hydrodynamics, and feedback from stars and black holes, to simulate the galaxy's evolution over cosmic timescales. By comparing these simulations with observational data, scientists can refine their models and gain a deeper understanding of the Milky Way's structure and behavior. The Milky Way's exploration also extends to its role in the broader context of cosmology. The galaxy's structure and dynamics provide important clues about the nature of the universe as a whole. For example, the study of the Milky Way's dark matter halo contributes to our understanding of dark matter and its role in the formation of cosmic structures. Similarly, observations of the galaxy's expansion and the distribution of matter help scientists study the effects of dark energy and the overall evolution of the universe. The Milky Way's search for extraterrestrial life is a particularly exciting area of research. The discovery of potentially habitable exoplanets within the galaxy has opened new avenues for exploring the conditions necessary for life. The study of these exoplanets, along with the search for biosignatures and technosignatures, has significant implications for our understanding of life beyond Earth. The Milky Way's diverse environments, ranging from star-forming regions to older, more stable regions, provide a rich context for investigating the potential for life and the factors that influence its development. As we continue to explore the Milky Way, we also face numerous challenges and opportunities. The galaxy's vast scale and complexity require sophisticated tools and techniques to study its various components and processes. The ongoing development of new observational technologies, such as next-generation telescopes and space missions, promises to reveal new insights into the Milky Way and its place in the cosmos. In summary, the Milky Way Galaxy is a dynamic and intricate system that offers profound insights into the nature of galaxies and the universe. Its structure, dynamics, and interactions with other galaxies provide valuable clues about cosmic processes and the distribution of matter. As we continue to explore the Milky Way, our understanding of its components and processes will expand, revealing new aspects of its complexity and contributing to a broader understanding of the cosmos. The ongoing study of the Milky Way reflects humanity's enduring curiosity and quest for knowledge, driving scientific discovery and inspiring future generations of explorers. The Milky Way Galaxy, an intricate and sprawling system, represents one of the most significant areas of study in astronomy. Its vast scale and multifaceted nature provide a window into understanding not only our own galactic neighborhood but also the broader mechanisms governing galaxies across the universe. The more we learn about the Milky Way, the more we can unravel the mysteries of cosmic evolution and structure. The galaxy's spiral structure, with its prominent arms extending from the central bulge, serves as a quintessential example of galactic morphology. These arms are not static but are the result of complex gravitational interactions and dynamics. Density waves traveling through the galactic disk compress gas and dust, leading to localized bursts of star formation. This process creates the bright, star-rich regions that characterize the spiral arms. The study of these arms, along with their interactions with other components of the galaxy, provides valuable insights into the mechanisms driving star formation and the overall evolution of galactic structures. The central bulge of the Milky Way is another area of significant interest. This densely packed region of stars and gas plays a crucial role in the galaxy's dynamics. The bulge is home to some of the oldest stars in the galaxy, and its study helps us understand the formation history of the Milky Way. Observations of the bulge reveal that it contains a mixture of stellar populations, including both ancient stars and those that have formed more recently. This diversity provides clues about the processes that led to the formation of the central region and its subsequent evolution. Central to the Milky Way's dynamics is its supermassive black hole, Sagittarius A star. This black hole, with a mass millions of times that of the Sun, exerts a profound influence on the surrounding stars and gas. The study of stars orbiting near Sagittarius A** has provided crucial information about the black hole's mass and the distribution of matter in the galactic center. These observations also shed light on the role of supermassive black holes in the formation and evolution of galaxies, suggesting that they play a central role in regulating star formation and galactic dynamics. The Milky Way's halo, an extended, roughly spherical region surrounding the galactic disk, contains some of the galaxy's oldest stars and globular clusters. This halo is a repository of relics from the early universe, and studying its composition and structure provides insights into the galaxy's formative years. The halo also contains a significant amount of dark matter, which influences the rotation curve of the galaxy and affects its overall dynamics. The presence of dark matter in the halo helps explain why the Milky Way's outer regions rotate faster than expected based on visible matter alone. The interstellar medium, ISM, is another crucial component of the Milky Way. This diffuse gas and dust, which pervades the galaxy, is the material from which new stars and planetary systems form. The ISM is not uniform but is structured into various components, including molecular clouds, HI regions, and supernova remnants. Each of these components plays a role in the galaxy's star formation processes and overall dynamics. For example, molecular clouds are the primary sites of star formation, while supernova explosions inject energy and heavy elements into the ISM, influencing subsequent star formation and the chemical composition of the galaxy. Observations of the Milky Way also reveal its interactions with neighboring galaxies and cosmic structures. The galaxy is part of the Local Group, a collection of galaxies that includes Andromeda, the Triangulum Galaxy, and several smaller galaxies. The gravitational interactions between these galaxies influence their structure and evolution. For example, the Milky Way's interactions with the Magellanic Clouds have led to the creation of tidal streams, features that provide clues about the galaxy's history and the processes that have shaped its current structure. The study of the Milky Way extends beyond its immediate surroundings to its place within the broader cosmic context. The galaxy is embedded in a vast network of cosmic structures, including galaxy clusters and superclusters. Observations of these structures help scientists understand the distribution of matter on the largest scales and the processes that govern the formation and evolution of cosmic structures. The Milky Way's motion through the cosmic web affects its interactions with other galaxies and the distribution of matter in the universe. The search for extraterrestrial life within the Milky Way is another exciting area of research. The discovery of exoplanets in the habitable zones of their stars has significant implications for astrobiology. The study of these exoplanets, combined with the search for biosignatures, indicators of life in planetary atmospheres, and technosignatures, signals from advanced civilizations, drives research into the potential for life beyond Earth. The Milky Way's diverse environments, from star-forming regions to older, more stable regions, provide a rich context for investigating the conditions necessary for life. Technological advancements continue to enhance our exploration of the Milky Way. Space missions such as the Gaia spacecraft have provided a detailed three-dimensional map of the galaxy, offering insights into the positions and motions of stars. This data is crucial for understanding the galaxy's structure and dynamics. Similarly, the James Webb Space Telescope, with its advanced observational capabilities, is expected to revolutionize our understanding of the Milky Way by providing new details about its formation and evolution. The study of the Milky Way is also closely linked to broader cosmic questions, such as the nature of dark energy and the expansion of the universe. By understanding the Milky Way's structure and dynamics, scientists can refine models of cosmic expansion and the distribution of dark energy. This research contributes to our understanding of the universe's overall behavior and the forces that govern its evolution. As we continue to explore the Milky Way, we are not only uncovering the secrets of our galactic home but also contributing to a broader understanding of the universe. The galaxy serves as a key piece of the cosmic puzzle, offering insights into the formation and evolution of galaxies, the distribution of matter, and the potential for life beyond Earth. The ongoing study of the Milky Way reflects humanity's enduring curiosity and quest for knowledge, inspiring new discoveries and expanding our understanding of the cosmos. The Milky Way's exploration is a testament to our ability to unravel the mysteries of the universe. Through advancements in technology and observational techniques, we continue to gain new insights into the galaxy's structure and dynamics. Each discovery adds to our understanding of the Milky Way and its place in the cosmos, enriching our knowledge of the universe and our place within it. As we look to the future, the exploration of the Milky Way will continue to drive scientific inquiry and inspire future generations of explorers, fueling our curiosity and expanding our horizons. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Subscribe to the channel for more such amazing videos.